dimensions. So, uh, manufacturers have developed heat exchangers of different sizes known as the mini and micro channel heat exchangers. And here you can see even smaller size. You can see this is the size of a needle, and here is a microfluidic device through which fluid flow occurs for different applications like drug delivery, mixing of drugs, etc. And now, what is the need for this small flow processes? You find out human being got inspiration by observing the natural micro level systems like your biological systems include um, brain, lungs, kidney, intestine, and blood vessels, from where man inspired and manufacture or develop such kind of systems like your heat exchangers, nuclear reactors, desalination unit, and air separation unit, where heat exchangers are very widely used for different purposes. And what is the function of heat exchanger? It has two objectives. First is bring the fluid in intimate contact with the channel wall so that there will be transfer of energy through the wall. And here you understand that the flow rate basically depends on the cross-sectional area, which basically varies linear with the square of the diameter of the channel. That's why the surface area to volume ratio is inversely proportional to diameter of the channel. So the smaller the diameter, the bigger the surface area to volume ratio, and the bigger the surface area to volume ratio, the bigger will be the or the higher will be the heat transfer. And here in this diagram, you can understand the range of different applications. Like it is very small, as small as 2.5 micrometer, as big as 25 millimeter channel diameters. And one very typical and very popular application is electronics cooling, where the dimensions lie in the range of 100 to 300 micrometers in this range. So, if you go to the literature, a microchannel is classified as whose hydraulic diameter is greater than 200 micrometer, but sorry, less than 200 micrometer, but greater than 10 micrometer. And when it is greater than 200 micrometer up to 3 millimeter, this is known as the mini channel. So, here in this talk, we will be talking about basically mini and micro channels. Here, this plot gives an idea how this heat transfer coefficient varies if we go on changing the hydraulic diameter of a channel. And for two different kind of fluids here. Here you can observe as you go on decreasing the hydraulic diameter of the channel, the heat transfer coefficient is increasing. Okay, so this is a good thing that for smaller hydraulic diameter, we are getting higher heat transfer coefficient, which will lead to uh, higher Nusselt number in the dimensionless representation. But this plot gives the idea that with decreasing hydraulic diameter, the pressure drop is also uh, increasing, which is a negative point of a micro scale devices. But this is a positive point of a micro scale devices. So here you have to understand that obviously there will be both positive and negative effects are there, but we have to understand the combined effect should be in the positive direction. That means the heat transfer for per unit pressure drop should be higher. Then only these heat exchangers are very useful, which have been already proved. So what are the advantages of this flow procedures? Basically, it helps to enhance the heat transfer. It increases the heat flow dissipation in the microelectronic devices, and these micro scale devices help for cooling of high flux devices. For example, today we are using supercomputers for doing the calculation at a very faster rate. But these supercomputers are generating a lot of heat which need to be removed, which is possible through the microscale heat exchangers only. And if you understand the contribution of manufacturing engineers, you can see different kind of manufacturing technologies are being adopted for developing microfabrication devices of different 1 micrometer to bigger scales like in the range of 1000 micrometers. Using ultra precision milling, glass etching, electrical discharge machining, laser ablation, micro machining of silicon, lithography, uh, E-beam lithography, X-ray lithography, and ultraviolet lithography, etc. So here you see this is a photograph of a typical mini microchannel test section where we find it very difficult to understand anything except that you can see one steel pipe and two steel pipes are there. So what we can understand here, fluid will enter into this system, let's say through this inlet, and fluid will leave through this outlet. So fluid goes here and there is a micro channel is there and it leaves here. So this is the direction of flow along the test section line. The channel dimension will be very small, so very difficult to see under the naked eye. But if you take a proper photograph in a good quality camera, you will be able to see. And this is the micro channel that is fabricated on a steel substrate. This micro channel is fabricated using laser micro machining. Again, thanks to manufacturing or production engineers. So here you can see, and this is the inlet to the channel, and this is the outlet to the channel. That means fluid will enter here from the bottom, and this fluid will pass through this channel, and it will move from the inlet toward the outlet. Then here you have a slot fabricated, created basically to insert thermocouples. And here, please understand, the thermocouples we are basically using for measurement of the temperature. And considering the size we have to use here, we will be able to use only the micro thermocouples only. So what is micro thermocouple? Basically, it is a thermocouple having the dimension, that is the diameter of the bead in the micron scale. So here you see, this is a channel. The hydraulic diameter was approximately 0.4 meter only. This is 0.4 millimeter. That means 400 micrometer. So from there you can get the idea that thermocouple slot is again around in the range of 600 micrometers. So the bead diameter should be less than 500 micrometers. So if you zoom in to this portion in a scanning electron microscope, so here you see the SEM image, scanning electron microscope image, where you can see this is the channel and this is the thermocouple slot here. So fluid is flowing here, and our objective here, understand, is to measure wall temperature. As the title of my talk is importance of precise measurement in microscale devices. So here you get the idea that our interest is to get the temperature here. So practically, our bead of the thermocouple should be here. But practically, this is not possible in an experimental scenario. So here we have made a slot for the thermocouple bead. So here will be your thermocouple bead, and these are the positive and negative wires of the bead. And here you see this gap is the smallest gap possible from the manufacturing point of view. We cannot further minimize this gap. So this dimension is approximately 500 micrometers. That is, it was the closest possible practically nearest to the solid fluid interface. I will try to place the bead of the thermocouple. And here you can see this is the sectional view of a microchannel under the scanning electron microscope. Again, you see the typical shape. This shape is neither a square nor a rectangle nor a trapezium. So very difficult where fluid is flowing through this channel here. Now we will learn here in this talk how important it is to measure two things here: wall temperature, that means it is in the solid domain, okay, and second thing is measuring the fluid temperature, that means it is for the fluid domain. So what we expect here is that we should be able to measure the fluid temperature at different points along the flow of across the channel. But practically this is not possible. So what normally experimentally people do, they will measure the fluid inlet and outlet temperature. Fluid inlet and outlet temperature. So if we want the accurate result, then the fluid inlet means we should measure here and we should measure here. But in reality, this measurement is done far away from the actual inlet point and the actual outlet point. For example, if you consider this diagram, maybe the fluid measurement is done somewhere here, we'll do it somewhere here and somewhere here, which is at a distance, reasonable distance, maybe 1 centimeter or something. So likely to lead a result maybe 10% or even more also. Secondly, our interest is to measure the temperature at the interface, but actually our thermocouple bead remains a small distance away. For example, here in this case, the distance was around 500 micrometer to 2 millimeter in this range. It was there. So here you see a experimental testing for this microchannel heat transfer. Very difficult to understand here. So that's why I have represented the overlapping the schematic diagram. You can see this is the microphone, this is the condenser, and this is the test section for this one. So it is not our interest here to discuss this experimental setup because we are now much more interested in the importance of the precise measurement. So basically, our measurements here will be temperature and pressure. So here you can see a data acquisition system that basically helps us to measure the temperature and pressure. For temperature, thermocouple is used, and for pressure, differential pressure transducer is used. So here, both will provide the signal in the form of either current or voltage. So there is a need for using a DAQ to convert this information into the desired value of temperature in degrees centigrade or Kelvin and pressure drop in terms of bar or the Pascal value. Again, for accuracy of measurement, we need a precise DAQ system that can have a high accuracy measurement capabilities. So now you see why this precise measurement is important because of a very difficult phenomenon in microscale heat transfer that is known as the axial wave conduction. So to understand this one, here I have taken a textbook figure. You will find out any standard heat transport textbook. Here you can see when fluid is flowing through a circular tube subjected to constant heat flux boundary conditions, this plot will tell you the axial variation of wall and the fluid temperature. And this is the plot when subjected to constant wall temperature. This is for constant wall flux and this is for the constant wall temperature where you get the wall temperature and the fluid temperature. So here you can observe when you provide a constant wall heat flux, the fluid temperature linearly varies between the inlet and the outlet. However, the wall temperature in the developing region does not vary linearly. It only linearly varies in the fully developed. condition, the fluid flow across the channel, the temperature is not linear in nature. That means it is non-linear in nature. Whereas the wall temperature is flat in nature because we have imposed a constant wall temperature boundary condition. Experimentally, what people do is while doing the calculation, they they try to interpolate fluid temperature at any external location. Why they do it? Because they apply constant heat flux at the bottom of the surface and they assume that. So this is important. Assume that constant wall heat flux is experienced at the solid fluid interface. At the solid fluid interface. So, but my experience says that in most of the cases, it is not true. Why it is not true that we will discuss later on. So, there they do a mistake. For example, if the actual variation is let's say something like this, and then do an interpolation and from the inlet, they calculate the temperature to this value, whereas the actual temperature to this value. So, because of this error in the measurement or calculation, there will be further error in the final outcome. For example, here we are interested to calculate the Nusselt number. So the value we obtain through calculation for the Nusselt number at any location will be different than the actual Nusselt number expressed at that particular location. So this is the mistake we do because of the improper or not doing the precise measurement in the statistical devices. So here we can observe because in this case of constant wall heat flux, there is a variation in the temperature along the axial direction. Let's say I take 2 points A and B. So the temperature at point A and temperature at the point B, and they are not same. So temperature at point B is greater than temperature at point A, because of which there is a driving force for heat transfer by conduction from the point B towards the point A. This will occur in the solid wall, heat transfer by conduction, and fluid is moving in this direction. So this is the direction of fluid, and this is the direction of so this is the direction of conduction in fluid, and this is the direction of conduction in the solid. And conduction occurs in a direction opposite to the direction of the conduction in fluid. That's why this is known as axial wave conduction, also known as axial wall conduction. So here you need to understand that when this thickness of the tube or the channel or the duct is small, then this area is small. But when the tube or channel thickness is more, then the area cross section of the solid is more. When the area cross section of the solid is more, in that case, the heat transfer and conduction will be more. Again, to understand in detail, you see here, what is the consequences we are having. I have taken the zoom view of a circular tube here. You can see this is the outer surface shown by this pink color here, on which we apply the heat flux and we apply the constant heat flux. And this is the inner surface represented by blue color. Some amount of heat flux is experienced. By default, normally we assume applied heat flux is constant, which is equal to same as the experienced heat flux. Practically, it will not remain same because both the areas may not be same. And our interest to calculate the Nusselt number using this expression Nusselt number equal to HDH where heat transfer coefficient H can be calculated by taking the flux value at the interface divided by the wall temperature and the bulk field temperature at that same location, and this wall temperature is also at the interface. That means here we see our interest is to calculate the wall temperature at the interface. This is important. Wall temperature at interface. But practically we cannot measure the wall temperature at the interface. So this is the point where we do the mistake. Normally people will measure the temperature far away from the interface and they assume and write this to be the wall temperature. And based on this they do the further calculations. And the accuracy further increases with increase in the solid wall thickness. So to understand this one, here you can see the actual photograph of different size and different shape dots, where you can see, for example, here the thickness is very high, and here you can see the thickness is very low. So wall thickness can have any range. Again, with increasing, with decreasing the dimension, here you can see the actual photograph of microtube cross sections using the scanning electron microscope. Where, for example, here you can see this is your the fluid domain, and this is your solid cross-sectional area for the fluid here. And if you consider this is your inner radius and this is the outer radius, so you can see outer radius here is greater than the inner radius, and the area of cross-section of the fluid domain is very small compared to the area of cross-section of the solid domain. That's why there is a scope for heat transfer by conduction in the solid domain, whose magnitude will be very high, and it can affect the axial distribution of flux at the solid fluid interface and the temperature at the solid fluid interface, along with the temperature of the fluid at a particular location between the inlet and outlet of the microscale device. So if you have any doubt at any moment, you can stop me and you can ask it here. So to understand this one here again, I am trying to explain here. For example, you see here, we are applying constant heat flux on the outer surface of a circular tube. What we assume, this flux will move radially. For example, when you apply the flux here, we expect that radially it will move to the inner surface. So this is the inner surface. Okay. Then from the inner surface there will be conversion to the fluid, and the fluid is moving, so the heat will be carried away by the fluid by means of convection. This is what we expect and we assume. But practically what happens? Practically, some amount of heat by conduction occurs in the solid region uh, in a direction opposite to the direction of the fluid flow. So practically what happens? Whatever heat flux I am giving here, supposed to go this way, but actually goes this way. That means in the solid it makes some axial movement, and from here it goes to the fluid by means of convection and carried away by the fluid. This has an implication on the temperature at different points at the solid fluid interface, which is going to affect the value of the heat transfer coefficient at different points along the flow direction, which will again affect the value of the Nusselt number and the overall heat transfer from a microscale device. In a circular tube or a circular geometry, this case is relatively less complex. However, in a microchannel fabricated on a solid substrate, this is how will be your sectional view, where we are applying the constant heat flux at the bottom, and the heat moves in the solid to the interface, and from the interface it goes into the fluid. So, for example, here whatever heat applied directly goes to the bottom phase, and whatever heat you apply here, it goes to the side phase. So this creates a very complicated scenario in the sectional view, further complicating the overall international process in a microchannel system. And this phenomena is known as conjugate condition, where the temperature distribution and heat transfer in solid and the temperature distribution and a heat transfer in fluid are coupled with each other. If one phenomenon is affected, the other phenomena is also affected. This will change the overall temperature distribution in the both solid and the fluid form. Normally, researchers they neglect this conjugate condition and they forget the role of the thickness of the solid, the conductivity of the solid domain, they do not consider. Because of which they do a mistake in interpretation of the or measuring the actual temperature of the solid fluid interface, the actual flux value experienced at the solid fluid interface, because these two values along with the bulk fluid temperature at that particular location is going to decide the value of the heat transfer coefficient H, which again going to decide the overall heat transfer value in a particular scenario. So next question is this: what measurements we normally do in a mini micro channel system? So here you can see this is the actual photograph of a mini channel array where you can see this is the inlet header and this is the outlet header and this is made from copper material and the thickness of this copper substrate was around 8 millimeter. And this hydraulic diameter was in the range of 1.1 millimeter and there are 15 number of channels. 15 number of channels. This is the inlet through which fluid enter and this is the outlet through which fluid leaves. So here, what is the simple assumption is made by the researcher is that the total fluid passes through the 15 channels at equal flow rate. That means the flow rate to each and every channel is assumed to be constant here. Based on this, research normally do the calculations. So here, what measurements basically we do? We go for the measurement of the temperature and the pressure. So to understand that one, you see how a microchannel is done. A substrate is considered, then a channel is engraved, then fluid will pass through this engraved volume, and we use a cover plate to seal this one. And here you see we apply the constant flux at the bottom. Okay, so this will be the sectional view, and this is the siding. And we apply the constant flux using a heater by attaching it at the bottom, normally it is dry heater, and we insulate the system to avoid heat loss from the system. So here fluid will enter at the inlet and fluid will leave at the outlet. So our interest is to measure the fluid temperature. Second interest is to measure the water temperature. So to measure the water temperature, what can be done? We can drill a hole here, and in this hole we will insert one thermocouple. So you can see this is the bed of the thermocouple. Then how many thermocouples you will install here? It depends on your requirement. Normally, how people install the thermocouple is that here on this side they will make they will drill holes in this direction. And in these holes they will insert the thermocouple. So this way they do the measurement of the temperature of the solid domain at different locations known as one temperature. Here I have represented TW1, TW2 and TW3. So the number may be varying. So some people may measure it 10 points, some people may measure it 5 points, some people may measure it only 1 point also. So basically what is your interest? We measure the fluid inlet and the outlet temperature. We measure the solid temperature at different extent locations as per the requirement. And here, how people normally place the thermocouple, they do not think much here. They simply randomly drill a hole here, and in the hole they insert a thermocouple, and after that you are supposed to fill this gap using a thermal paste or high conductive paste should be used so that this void space can be filled with a solid. This will avoid the thermal contact. So you see here, this is our channel, solid fluid interface. Our interest is to get the temperature here at different locations. But wind is measuring the temperature at a small distance away. Even sometimes people does not bother to know the exact location of the wind. Sometimes they randomly do this way, or sometimes they randomly do point and this thermocouple goes up to this point. That means we are measuring the temperature only at 2 points in the SL diagram below the channel. So this is the channel, below the channel we are measuring. But actually our requirement is that we should know the temperature at the solid fluid interface. That means here we are not doing a precise measurement of temperature. So the inaccuracy in measurement may lead to different conclusions. Or we may assume the outcome is totally different than the conventional side heat exchangers. So now question arises, how experimentally average Russell number is calculated in micro channels? To understand that one, we take this mathematical expression N equals to HCl by KF, and H is the conductivity coefficient, that is equal to flux divided by wall temperature minus the fluid temperature. So here that can be written here, that will give you the expression for the Russell number, and here we BH is a constant value, KF is a constant value. That means here we require the wall temperature, we need the fluid temperature, we need the flux value. So what is this three are? Normally how people do the wall temperature measurement? They will drill holes in the axial direction in the solid at some random locations. They will insert the thermocouple, they will take the reading of the thermocouples represented in TW. So if, let us assume 3 thermocouples are used. So wall temperature they calculate by taking the average of these three holes, direct straight average, TW1 plus TW2 plus TW3 by 3. And how they do the, so generally we can represent mathematically like this, 1 by n sigma equals to 1 to n TWI. So n is the number of thermocouples inserted in the solid. Then for fluid temperature, what they do, they take the fluid temperature at the inlet and outlet and they simply take their average. That they call as the fluid temperature. And for the flux value, so practically we attach one heater, a stripe heater in the bottom. So this is the positive and negative terminals. So we can measure how much is the current drawn by the heater here. And this is the width of the stripe heater, and this is the length of the stripe heater, which is nothing at the diameter of the base. So accordingly, the heater is considered to provide constant heat flux at the bottom. So the flux we can calculate it, the heat supplied by the heater multiplied by the area of the heater. That is the area of the base, that is equal to W into L. And the heat supplied by the heater is nothing but power P equal to G into I. So B is the potential difference applied across the two terminals of the heater, and I is the current drawn by the heater. So from this formula, the flux value is calculated by the majority of heat. Okay, but practically what is happening, you have to understand, this kind of measurement and usage for calculating Nusselt number is totally wrong. Why? To understand that one, you see, when you apply heat at the bottom, it moves towards the interface. So here this is the interface. And top one we consider to be the insulated purpose. So heat enters to the fluid through these three interfaces only. So what is happening? The heat is going to the interface by crossing different paths here, and at the interface, the heat enters into the fluid by means of convection. So here, what you basically need, the flux is the average flux at the interface, which is different than this flux value. And this wall temperature, this is also different than the actual value. So wall temperature is again the peripheral average of the wall temperature along the solid fluid interface. And the bulk fluid temperature is the average of the temperature at the sectional view. So, how the average, let's say we have to calculate the average Nusselt number, how should we calculate it? So here, whatever calculated, people assume this to be the average Nusselt number, which is a totally incorrect way to do the calculation. The ideal way to do the calculation for the average Nusselt number is like this. So here, in the expression for this Nusselt number, this is a local value. That is local Nusselt number NU Z. Z represents local value, it is any position along the length of the flow, that is equal to h z into dh by k. So dh and k is a constant. Again, h z is the local heat transfer coefficient. It is for a particular location. Okay, so that will be the local flux at the interface, the local wall temperature at the interface, minus the local ground fluid temperature at the section. So this Z can have any value starting from Z is equal to 0 at the inlet to Z is equal to L at the outlet. So here, when you apply the flux at the bottom, the heat moves towards the interface and it reaches to the interface. The interface is shown here by this peak line here or red line here, and uh, the temperature at each and every point at the interface will be different. So ideally, the wall temperature should be the average of all the temperature values, and the flux temperature at the interface should be the average of all the values, and the bulk fluid temperature should be average of all fluid particle temperatures in the whole domain. But experimentally, this is not possible to calculate. However, we can take steps to have the closest possible value. However, if you are doing a numerical simulation, this is possible. So, what to do? The flux temperature to calculate by taking average of the flux value at all the points at the solid fluid interface, and then the averaging should be done by taking the area weighted average. For example, if you are using the software called axis student, then you should consider the area weighted average of the flux value at each and every point along the solid fluid interface. That will give you a single flux value, which is a local flux value. That is correct only for a particular position. For example, we are doing it, let's say z is equal to 0.25 L. So at this location, for that particular year, we are calculating the local flux value. Similarly, local wire temperature will be average of the temperature at all these points, and this averaging is done by considering the area weighted average for the wire temperature. And this for bulk fluid temperature calculation, that is PW, it should be the mass weighted average of temperature of all the fluid particles at that particular frictional location in the fluid domain. So this is the ideal way to do the calculation. So if you are going to use a simulation, you should calculate the local Nusselt number this way, and for experiment, you should take steps to get the precise measurement that again I will explain next year. And after that one, the average Nusselt number can be obtained by taking the plot for the local Nusselt number that will form a curve, and the area under the curve divided by the length of the domain. Length of the domain is L. That will give you the average Nusselt number, which can be calculated very easily. So mathematically, the average Nusselt number can be represented as NU bar, that is equal to 1 by L integration of 0 to L NUZ dk, where NUZ is the local Nusselt number. Practically, we see if I could plot it, the local Nusselt number plot, you will get something like this. So here it is NUZ, and this is a Z. So this is Z is equal to Q to Z equal to L here. And the average Nusselt number value will obtain something like that. So this is the NU average value. And you can see here in the fully developed region, the Nusselt number value will remain constant. So now we will come to the discussion part. Here we will consider a single phase heat transfer and fluid flow in mini channel array. For example, experiment was conducted in this mini channel array, and what difficulties we encountered and how these difficulties sorted out we will discuss here. So here you can see the micro details how fluid enters to the inlet through the bottom here, and how it leads to the outlet here. For example, you see fluid will enter from the bottom, and this is the channel header, and from the header it goes to the channel, and again it is the outlet header, again it goes to the bottom. So be slightly more than the less than the actual temperature at the inlet of the fluid. This is because the fluid gets preheated before it reaches to the actual inlet location. So this to be ensured here. Second challenge is getting the flow rate at each and every channel. No such divide exit that can provide flow rate at each and every channel. So normal practice is that you take the inlet flow rate that divided by number of channels is the amount of fluid flowing through each channel. Best known, we calculate the Reynolds number in each channel, which is an incorrect way because you see from numerical simulation it is proved that there will be a flow multiplicity.
वीडियो में कुछ हो गया ना वीडियो में some issue with it.
ये उनके नेटवर्क प्रॉब्लम
Are you getting my voice?
Voice, it's okay, it's okay.
Okay. Are you able to see my screen now?
Yeah. I'm able to see you. Now you can share your presentation.
Can you see my screen now?
Yeah, it's coming up. It's loading up. We can see it.
Okay. So, from which screen slide you are not able to see? Should I start from here or it will be fine?
From this you can start.
Okay, fine. So here you see in this mini channel which contains 15 number of channels, practically it is impossible to find out what is the flow rate in each and every channel. But experimentally people do, they take a total flow rate divided by 15 that they consider flow through each channel. And based on that, they present the calculation, which is not the realistic value. The reason is, from simple common sense also, we can tell that the amount of fluid that will pass through every channel will not be same. Because you see here, the central channel, there will be the maximum flow rate because it is the shortest path, and the extreme end channel and the flow path distance is the maximum. That's why the minimum amount of fluid will flow through the extreme channels. So to understand that one can do a very simple analysis of numerical or CFD modeling, and through which you can find out what is the value of the actual flow rate in each and every channel. For example, here we simulated the 50% of the channel because the symmetry on this part we simulated. So the central channel is number one, extreme outer channel is the number eight. So you can see for number one channel, for every mass flow rate, you are getting the highest value here, and you are getting the lowest value on the extreme left or the extreme right channel. So through a little bit of simulation, we can find out the flow rate in each and every channel, and further calculation should be carried out based on the actual flow rate in each and every channel. So next we consider the investigation of axial wall conduction and axial bed conduction. How wrong interpretation of the results leading to a wrong outcome. That we see here. So since practically we cannot measure the temperature at the solid fluid interface, we are measuring the water temperature far away from the interface. We are not getting the actual scenario outcome, so our interpretation becomes wrong. That's why we took the help of CFD simulation to understand this one. So here we consider a square microchannel fabricated on a rectangular substrate, and we considered single phase heat transfer, and we carried out three-dimensional numerical simulation. And what was our interest in to understand what is the effect of the substrate thickness. So this is the substrate thickness. So we define it like this. Substrate thickness is sum of delta S and delta F, where delta S is the height of the fluid domain, and delta S is the thickness of the solid below the fluid domain. So total substrate thickness is delta S plus delta F. Then we define a dimensionless parameter delta SF, that is ratio of delta S and delta F. Prandtl number represents dimensionless thermophysical properties. Then we vary the conductivity of the solid, while here we have taken water as a fluid. So conductivity of the fluid remains constant, and conductivity of the solid is varied, such that the ratio of Ks and Kf represented as Ks varied very widely, starting from very small value of 0.34, which corresponds to very low conductive material, to very high conductive material like copper and silver, for which Ksf is very high, 700, and the flow rate is also varied in the range of Reynolds number 100 to 1000. And all the information are converted into dimensionless form for better understanding. And here, one important parameter we have defined is phi. What is phi? Phi is nothing but the value of flux experience at solid fluid interface divided by ideal flux. Ideal flux means the flux that should be, that means theoretical flux at the interface. Now question is the theoretical flux at interface same as the flux applied? The answer is actually no here. Why? Because you see, for example, in this geometry, I am applying, let's say, some heat Q here. So Q divided by base area, that will convert into a flux that is applied. Okay. But the flux here will again depend on the interface area. So what is the ideal flux at the interface? That is equal to flux applied is equal to the amount of it that passes through the interface to the fluid. So based on this, we will obtain the ideal flux, and the actual flux can be measured from simulation, and the ratio of the actual flux to ideal flux will give you a value phi. And if the phi equals to 1, that means it is ideal condition, it is expected. There is no distortion in the flux at the interface. If phi is not 1, that means there is a distortion at the flux at the interface. Okay. So here you can see the axial variation of, I will make the zoom of these figures, axial variation of the dimensionless flux here, phi. So here you can see, this is the inlet position, this is the outlet position, so it is the axial direction. So everywhere it is remaining 1, indicating that the amount of heat you apply here at the bottom per unit area, and the amount of heat that passes through the interface per unit area throughout the length is same. That means there is no axial conduction in the solid. Secondly, also there is no effect of thickness. When you change the thickness, then also the flux does not distort here in this case. This is a case corresponding to low case, 0.8 for low RE, even for the highest. Then we have considered the extreme highest conductivity value KSF. Here you can observe the values are not remaining constant of 1 throughout the length. For some length from the inlet, it is becoming above 1, and for the remaining length, it is becoming less than 1. Secondly, depending on the thickness, the values are also changed, indicating that there is a presence of axial conduction, and the flux is not constant throughout the length. So experimentally, what people do, they use a heater at the bottom and they assume it is constant throughout the length. They select some random dimensions for the thickness of the substrate and the material of the substrate, which is not correct. As indicated from this plot here, you can see high conductive material is leading to axial wall conduction, that is causing heat flux is not constant in the interface, and also higher thickness, substrate thickness leading to higher distortion. So this is what you can conclude from this plot here. Then we go to the next plot. That is for axial variation of dimensionless bulk fluid temperatures and the wall temperature. So here you can see this axial variation of this is your wall temperature and this is your fluid temperature, which is same as the textbook plot. Indicating that the flux at the solid fluid interface here is constant here throughout the length of the flow. And here you can see the straight line portion is decreasing. This is because in this direction Reynolds number is increasing. The higher the Reynolds number, the higher is the developing length. So this developing length is increasing. That is the reason. That means here for all the cases there is no absence of axial wall conduction, which leads to uniform or constant heat flux throughout the length, which is good and which is actually our requirement also. However, here you can see this is a set for high conductive solid material, for which you see here, and now here the fluid temperature is no more linearly varying. Ideally, the fluid temperature should vary between inlet and outlet like this, but actually the fluid temperature is very something like this. That means if you take a linear interpolation for the fluid temperature at any location, the actual fluid temperature is this one, but we consider the fluid temperature with this one. That means here you do a measurement error of this value is the fluid temperature itself. Similarly, the water temperature also does not remain linear in the fully developed region also. So we do a mistake in interpreting the water temperature that means you do a mistake in interpreting the wall temperature and fluid temperature by selecting improper thickness of the substrate and the material for the substrate. What is improper? By considering more substrate thickness and higher conductive material. Normally, people use copper as the uh, metal for microchannel substrate with the notion that copper is good for higher conductivity, good for heat transfer, so it is good for heat transfer application. But actually, this is not correct. Then to support this theory, we can further move to the Russell number plot, where you can see uh, the theoretical Russell number values we can find out here. That is the Russell number in the fully developed region case. For here we have considered square channel, for which if you apply constant flux, the value will be 3.556. If you apply constant temperature, the value should be 2.7. And here in this case, you can see the Russell number plots are also we are getting some changes here because there is the effect of the wall thickness along with the conductivity. So here you can see for low conductive we are getting a straight line, but for high conductive we are getting there is a downfall in the fully developed. So from here, we are getting a clue that the higher wall thickness and higher wall conductivity materials are creating problem for the ideal condition of obtaining constant flux. Then when you calculate the average Nusselt number, for example, you see this is how the local Nusselt number will vary, and the area under this curve divided by the domain width. So this is the domain width, and mathematically nu bar is equal to 1 by L integration of 0 to L nu z dz. That will give you this average Nusselt number value, which will be higher than the fully developed Nusselt number value. If we calculate this value, because we calculate the heat transfer based on the average Nusselt number. So in this plot, we have taken the average Nusselt number with respect to the conductivity of the solid represented as KSF in the dimensionless form. For very low conductive material to very high conductive material, for two thicknesses of the substrate, delta SF 1 and 60, and two extreme Reynolds number Ali 1 and 140. So here you can see with increasing conductivity, the average Nusselt number first increases drastically. It reaches to a peak value, and after that, if you further increase the conductivity, the average Nusselt number is decreasing. That means at a particular case here, we get the maximum average Nusselt number. So this indicates that there exists an optimum average Nusselt number at which heat transfer will be maximum. And this the corresponding material for optimum average Nusselt number is the optimum material for higher heat transfer in a microscale heat transfer device. With increasing thickness for particular Reynolds number, you can see there is a decrease in the average Nusselt number at any conductivity. And with increasing flow rate, the Nusselt number, average Nusselt number value at any KSF and any delta SF is increasing. Why it is increasing? Because higher RE means higher WPN, higher WPN means higher average Nusselt number. Then to understand why it is happening, we will now focus on the sectional view. So you can see we are applying the heat at the bottom, but the calculation is based on the flux at the interface and temperature at the interface. So here you can see for a wide variety of materials, the variation in the flux value along these three edges A, B, B, C, and CD are varying in a very erratic manner. For example, for few materials at the corner B and C, you are getting the maximum flux value, and for few materials, you are getting the minimum value. This is because of a complicated two-dimensional temperature distribution in the sectional field. By considering two extreme cases of low material and a high conductive material. You see, these are the isotherm flows. That means the normal to the isotherm will provide the direction for the heat transport. So here you can see we are getting more heat entering into the corner here. That's why this kind of temperature flux variation along the interface AB, BC, and CD we have obtained here in this case. Then we are interested the understanding the Excel bed conduction. So we have taken a transverse section, and in the transverse section we have plotted the isotherms. This is for high conductive material. This is for the extreme low conductive material. This is the intermediate conductive material. So here you can see this is the solid region, fluid, solid, and fluid. So a normal to this isotherm will give you the direction of heat transfer. That is, whatever heat I apply here, it goes this way. We expect it will go to here, but there is a small shift to the right hand side. This is the direction of fluid flow. That means here there is a small axial wall conduction present, but here you can see the direction of heat transfer will be this way because the isotherms are vertical. So whatever heat I apply here, I expect to go to the interface this way, but actually it is going this way and maybe reaching somewhere here. Because of which here higher axial wall conduction, more heat is entering towards the inlet region. That's why at the interface the flux will not remain constant. That's why higher conductivity is not recommended. Whereas for lower conductivity material, you can see here the flux will vertically move upward so that here at the interface you will have a constant heat flux condition because the average Nusselt number is higher for constant flux condition compared to a constant temperature condition. Whatever may be the shape and the dimension of the channels. So this was all about a square microchannel fabricated on a rectangular substrate. If you consider microtube, what will happen? That means we are applying constant heat flux on the outer surface to microtube. Then what happens here? The overall phenomena same. Here you can see. Here we have taken the average Nusselt number and varying with the conductivity. Here also the same thing. The with increasing conductivity, average Nusselt fast increases. It reaches to a peak value. Then it starts decreasing. Again, depending on the thickness, for example, you see here these two are for higher Reynolds number of 1000. This is for deltas of 1 and this is for deltas of 60. Here that there is a drastic drop in the average Nusselt number with increasing thickness of the microtube. So the overall phenomena remains same whether it is a microtube or a microchannel. But only thing is that in a microtube, the sectional view phenomena is relatively simple, whereas in a microchannel, the sectional view heat transfer phenomena is relatively complex in nature. So now we have to understand what is its practical implication. What is the practical implication? So if you do not get constant flux at the interface, practically how it is going to affect? You have to understand it. For example, you can see here, this is a research work published in 2012 by Chien et al. What basically they say is that they studied a process known as methanol steam reforming for the purpose of developing hydrogen gas through some chemical reaction. So there also they have concluded that axial heat conduction in the reformer valve played important role for both heat transfer and methanol steam reforming of turbines. The axial conduction was justified because of different types of materials they use, and they found that the conductivity has an impact on the amount of conversion to the steam here by the methanol steam reforming process. So here you can see the actual heat supply for the methanol steaming was reduced as the axial conduction parameter increased. As a result, the gas mixture temperature cannot be raised to a high temperature and methanol steam reforming performance is poor. So please note down in a steam reforming process, the presently in methanol synthesis process, methanol plus water is mixed and is heated to a high temperature around 600 degrees centigrade or 873 Kelvin, and this mixture steam will flow over a layer of catalysis. There will be a reaction, and that will produce the hydrogen gas, which can be used in a fuel cell to run a electric vehicle. And if the temperature becomes less because of excess conduction, the reaction will not be proper, so the conversion efficiency will be less, and a less amount of hydrogen gas will be produced for the particular case. That's why this is a practical implications also in the real life. So this is all about the first part. Uh, Depending on the feedback of the listeners, we will move forward. If you have time, we can discuss questions, or if you feel still more time is there, then I can continue.
We have 15 minutes for this talk.
Okay, thank you. Then I will may go for 7-8 minutes only. Then we will have a discussion. Okay, thank you. So then next we will see how the sectional geometry is going to affect this axial wall conduction. To understand that one, for the rectangle only, we may change the aspect ratio here, the width and the height here. Width is represented omega, height is represented delta here, in different manners, by maintaining that area constant, by maintaining the heating perimeter constant. Heating perimeter means these three lengths, some of the three lengths, because heating is done for the fluid through this interface only, so this interface length will maintain constant here. Okay, and by maintaining the width constant and maintaining the height constant. So manufacturer will understand fabricating a wider microchannel is easier, but fabricating a less wide but more depth channel is difficult. So higher depth channel is difficult to fabricate, but higher depth channel is easier to fabricate. So that's why we consider this four scenario, and the result indicate that for every scenario the variation of Nusselt number is the same with conductivity, that there exists a optimum conductive material that will get the maximum Nusselt number. Further increasing conductivity, Nusselt number decreases. But regarding aspect ratio, a very interesting result is obtained. If you go on increasing the aspect ratio, what is happening? uh, there is a particular aspect ratio at which you get the maximum value. That means it is like this. If I take aspect ratio this way and the Nusselt number this way, so it is the float is getting empty. With increasing aspect ratio, average Nusselt number is decreasing. At a particular aspect ratio, you are getting minimum Nusselt number, and beyond that, again it is positive. So it is a minimum Nusselt number we are obtaining corresponding to aspect ratio 2 here. Here also corresponding to aspect ratio 2, and uh, here you can observe for different conductive materials. Again, when we get it out, here also you observe, here we get the minima for 2, here also we got the minima for the 2, here we got the minima somewhere near 2, and here also the minima somewhere near aspect ratio 2. For the lowest conductive material, highest conductive material, and the material at which the Nusselt number is maximum. That means for every kind of material, it is observed that aspect ratio plays a role, and for a particular aspect ratio, you obtain the minimum Nusselt number. And if you go this way, Nusselt number is increasing, you go this way also, Nusselt number is increasing. But this way, if you go, the Nusselt number is more compared to you go this way, the Nusselt number is less. So accordingly, one should select the best or the optimum aspect ratio, so that we can have the maximum average Nusselt number. For example, you see, if I take aspect ratio 0.5 and 2, sorry, 2, it is, for example, if it is 0.5 means this will be 2 here, and this is easier to manufacture, and this is very difficult to manufacture. However, both will give you to same average NU. So if both give same average NU, why not you manufacture this one? Why by mistake you manufacture this one? So this kind of scenario should be avoided and proper decision should be taken. Now to understand what is its practical implication, here is a reference from 2012 where it says optimized geometries have much greater channel height compared to the channel width. The same thing also presented by other people. Because of that one, you can avoid a scenario where you have lower value of average muscle number. So I think with this I will conclude the talk here. Now I am ready for taking the queries from the listeners. So thank you all for a patient hearing.
Thank you, Dr. Manoj. Audience, please ask for the questions. You were having some questions. Yeah, come here, come here. You have to. पहले introduction कीजिए ना। Sir, I'm a student from Kashmir University, B.Tech Mechanical student. And the question is, you have mentioned about the bit loud, bit loud. What type of data acquisition system have you used? Actually, Manoj is asking you what type of data acquisition system you have used. But
Okay, basic. You see, as I told you, precise measurement is important. So good quality DAQ is very important. If you now do a market survey in the market, you will find out. For example, you want to measure temperature continuously. Continuously, we need a electronics DAQ system. You can get it for a 15-20,000 also you will get, and the good quality ones cost you 3 lakhs, 5 lakhs, even 10 lakhs. Like Agilent is a company, very good brand. But I personally use NI, National Instruments brand DAQ system. So it will be an intermediate cost, but it will provide very good quality and precise measurement.
the next question is bit loud. Inner roughness of channels you have mentioned, circular channels, cylindrical channels. Inner roughness. What is the inner roughness? He's asking you what is inner roughness in circular channels.
So the channel roughness. Channel roughness, actually, this basically depends on the manufacturing method you laid out. In our case, we measure the channel roughness to be approximately around 30 micron. That is 30 micrometer we obtain.
Dr. Manoj, do you use E by D ratio for channel roughness? If you have to just specify it, E by D, relative roughness height.
Actually, I see, actually, in experimental, we have done little bit experiment only because of practical difficulties. You have pointed out very correctly, it should be epsilon by D should be represented.
Yeah.
But that we have not used it. So if you can do a simple calculation, if you do it 30 divided by 400, so you will get 3 by 40. So 3 by 40, you will get the value. Let me do the calculation here.
Dr. Manoj is having another question. Just
You will get 0.075.
Okay, okay. Any application for stair channels type of heat exchanger? He's asking you real world application for what? Stair channel heat exchangers.
Square channel heat exchanger.
Where will you find those things? Huh?
Okay, there are a lot of applications. Actually, this microchannel heat transfer field developed initially for electronics cooling. What is electronics cooling? Cooling high computing devices. For example, your institute computer center must have a server. If you go to there, you find out they will have a very good cooling system. If your system is not cooled properly, your workstation and server will be bad. So the major application is electronics cooling. Nowadays, there is another field that is known as solar photovoltaic cooling. The theory says that the higher the sunlight you get intensity, the more the energy you will extract. Okay, this is one theory. But the other theory is that if the operating temperature of solar cell is low, then conversion efficiency is high. That means we want our solar cell to remain in sunlight, but we want it to be at lower temperature. Of course, Kashmir using micro channel so that operating temperature will be less, but you get high intensity sunlight so that you will get more electricity from the sunlight. This is one application. Then there is another application that is emerging application is electric vehicle battery cooling. So battery thermal management is another topic. This is a very hot topic now.
Dr. Manoj, which fluid you have used in your this analysis? Which fluid? What
Actually, we have used pure water, we have used pure ethanol use, and now we are working on ethanol water mixture because this mixture has application in hydrogen generation to be used for fuel cell.
So we can use this in future. We can use this for nanofluids also.
Yeah, nanofluid, we have also used nanofluid. So, silver-based nanofluid we have used in one case.
Okay. So it's a very good talk. One of my students is using the photovoltaic thermal collectors. He is just trying to cool that thermal collector by many channels, and he's just circulating nanofluid through those channels. Serpentine.
Oh, that's very good, very good. So then we can have a discussion sometime.
We can have a discussion.
Sure.
So, inshallah, I'll invite you next time. All in
Sure,
offline
sure.
session. Offline session. Huh? We'll have a detailed discussion.
I will be happy to meet with you and your students and make discussion in person.
Anyone else wants to ask? Now, if you want to ask, tell here. So, on behalf of mechanical department and organizing committee of this workshop, I am highly thankful to you for just devoting your precious time.
Okay, thank you, Professor Adnan. So I am very happy to be a very bigger audience. So more than 30 people are there in the audience. So
I can give you
I wish
I can give you a digital moment too. So it is with
sure,
me.
sure.
Your digital moment is with me, huh?
Thank you.
So when you come offline, I will give you this. This is with me. Your memento is
Sure,
with me.
sure. My best wishes with all your young researchers. So I hope they will do great work in future. Thank you all.
Thank you. Okay. Okay. Bye bye.
Bye.
यार कोई नहीं होता है कुछ नहीं होता है मुझे बीच में बंद करना पड़ता है
Next, we have Dr. Deepak Sharma. He has done his MTech from NIT Surat, PhD from IIT Kanpur. Currently, he is Regional Application Manager in TSI Instrument India Private Limited. He will be talking about laser-based techniques used in experimental fluid mechanics. Dr. Sharma's research interests lie in the area of fluid mechanics, and he has extensive experience in using laser-based techniques for experimental measurements. I request Dr. Deepak Sharma to deliver his lecture on the topic.
Chalo.
Yeah, thanks.
Dr.
Yeah,
Deepak, go ahead.
thanks for the introduction and very good morning to all of you. Hope it's a summertime in Srinagar, so
It's
it's no more
springtime.
snowing.
It's not summertime, it's springtime.
Okay, so I thought snow is getting melted, so we can talk about fluid mechanics.
Okay, that's fine.
So I need to understand, as far as the audience is concerned, are they from mechanical, BTech, MTech, or
That mechanical, that MTech mechanical engineering, thermal engineering. Many of them are
thermal engineering?
PhD students also. And so we have several participants who are faculty members of other institutes also, working in
Okay.
mechanical and this thing.
So how good that they can also interact with me during the
They can, they
presentation?
can. Fluid mechanics involves everything.
Okay, so they have the microphones to
It's
talk.
it's on. Actually,
Oh,
we are in the high tech this thing.
that's great. That's great. So
Auditorium.
thanks, thanks.
So
So I would
they
like
can
that
chat with you.
everybody should participate in it, and if you have any doubts, please let me know. And if I have doubts, even I will let you know.
Okay, that's fine.
So let me put up my slide. I can share it. Yeah.
Just click this hide button because hide is showing.
Uh,
Hide
Hide button.
mute
Okay.
now it's good. Now you can maximize it or but everything is fine. Yes.
So this looks good.
This is good.
Yeah, except my photo. So yeah. So yeah, guys. So we would be more talking about uh, how are we when we do experiments in fluid mechanics. Ideally, we try to tap some physical or physical properties which you feel that is important to analyze a particular flow. Flow can be in water, flow can be in air, it can be any gaseous flow. So I would like to understand the current status of our students that when you talk about experiments, what are the properties you primarily think that you want to like to measure? Yeah, what are the quantities or properties? Any of you can tell one or two or yeah. I want that. There should be some interaction. This is a simple question. It's not a question also. So yeah. So whenever you want to do an experiment in fluid mechanics or any research in fluid mechanics, or maybe you're just measuring what is the water collected in a tumbler, what are the quantities you're looking for?
Velocity is important.
Yes, velocity is one parameter. Any other parameter?
Density, viscosity,
Yes. So density, viscosity, pressure,
pressure,
flow rate,
because we want to have a
temperature,
live discussion.
right? And in terms of water or whatever it is. So when we talk about fluid, so essentially you try to tap velocity, and you try to tap pressure. Any devices you know by which you can measure pressure? I just want to understand. Or velocity, or flow rate.
Manometers.
Manometers, yeah, that's good. So manometers are there. So essentially, what do you measure in a manometer? You try to tap maybe the static pressure and the total pressure and you try to tap the difference, which is the dynamic pressure. So essentially, you are measuring dynamic pressure that later on you are converting into velocity. Okay, so by using manometer, you are trying to know what is the dynamic pressure. You might use a pedostatic tube inserted in the flow, and you know what is pedostatic tube? So it measures two pressures. One is the total pressure or stagnation pressure, and the on the periphery there are holes which gives you static pressure, right? So and the difference you're using YouTube manometer or any digital manometer and so on. So essentially, pedostatic tube you have inserted inside the flow. Okay, you may feel that okay, I'm measuring it very precisely, but when you talk in terms of research, you're actually obstructing the flow with that pedostatic tube itself. Although it is designed in a way that there's not much of blockage, this petod tube should not much hinder the flow, but it will. Secondly, you have aligned the pedostatic tube in a right angle manner in front of flow, in line with the flow. Accidentally, somebody shakes it and there's an inclination in the pedostatic tube. Then, what will be the reading? Will it affect the reading or not? Initially, yes, the it is facing the flow, but there is some inclination. Say somebody accidentally moved it by 10 degree or 5 degree. So, do you expect there will be some change in the manometer or the velocity? Yes, we feel that yes, it's not in line, so it has to give us a different value. That's absolutely fine. But I would like to let you know whether you've studied or not. Up to 10 to 12 degree of variations in pedostatic tube, there is no change in the manometer reading. So just imagine that you are moving the pedostatic tube by 10 degrees or 12 degrees and uh, there is no change in the velocity. So it's not at all sensitive device. So what I'm trying to highlight here is that it's a good tool to measure an average velocity, but it is not a sensitive tool to give you a local velocity at a location because 10 degree is too much of displacement or rotation, but still there's not much significant change in the actual values. So next time when you do an experiment with without static tube, try to notice this. Any other device you have come across apart from without static tube? Something which you don't want to insert inside. Without static tube you are inserting. Are there any other ways without putting anything inside can you measure flow? The average flow velocity. No, no, I'm not. That is my topic. Don't tell about I hot wire, yes, but again we are inserting something inside the flow. If you might have heard venturimeters, okay, orifice meter. Okay, so these are also devices which actually measures the flow rate. And if you know the cross-sectional area where you're measuring it, you can know what is the velocity. So these are good devices you're not inserting inside and you can know the velocity, but those velocities are average velocity. It's not a local velocity at a particular point. Okay. So again, without inserting hot wire is a good tool. It's the best tool I may say. But then again, you have to insert the hot wire inside the flow. It's very much sensitive to the flow. A very good device, but any any dust particle in the flow can damage the probe and it can break immediately. Myself and Professor Adnan, we have repaired so many hot wires during our PhD days. So we know how sensitive those wires are. So we have to be very much cautious about it. The other way which somebody said about PIVs and LTVs, yes. So that's how laser techniques were introduced that can we really use some other light source which goes inside the flow and there is some physical property change by which we can tap the velocity? Then yes, laser had that answer. So it has been a long years of research to figure out yes, we can really measure the flow properties like velocity, like I may say sizing of particle, and so on that can be neatly captured by using laser. Best part of the laser, it's a light source, so it's not blocking the flow. Okay, how does it measure and all that? I will give you a small introduction on that. So let me get started. I'm still on the first slide. So, anyways, so I work as a senior regional manager at TSI Incorporated. We are based, our headquarters is in Minnesota, United States, but we have our India office in Bangalore. Just a small introduction to the company. How TSI began. So, in the right side, you see a picture of Mike Fingerson. When he was doing his PhD in late 1950s in University of Minnesota, he had some topic to measure turbulence in a combustion chamber, and he figured out that it can be measured by using a hot wire and at a constant temperature. So that is a CTA. So constant temperature anemometry was actually, he was amongst the pioneer researchers to discover that a hot wire or a CTA can be used for measuring flow or the turbulence within the combustor chamber where he was working. So he cooled that combustion chamber to retain the constant temperature and noticed this thing. When he completed his PhD, yes, he had a good idea. He collaborated with few of his friends and established this company called TSI. That time it was named as Thermo Systems Incorporated. In 1961, he established. And unfortunately, sadly, he just passed away in month of Feb this year. So I used to write that we still sell CTA, but that was his product. Now it's a diversified company with multiple products. So we are still selling CTAs. Okay. So we are based at 8 to 9 locations globally. These are some product range in which TSI gets involved. We are here, fluid mechanics. So you may see that we have various divisions, but primarily we'll talk about fluid mechanics and the laser-based techniques. Okay, so I just wrote some motivational line why we want to study fluid mechanics or what is the topic all about. So by using lasers, you can do LDV, PIV, you might have come across this word, LIF, volumetric PIV, and so on. Okay, so let's begin with the laser. This picture shows some silly ape man. Some in the first picture it's leaning, second picture it's somewhat straight, and third picture is too much of straight. So here what I want to tell you is that the first one is a point measurement, second one is a planar measurement, and third one is a volume measurement. Point measurement means there are two laser beams which are intersecting at a point. When I'm moving my cursor, can you see the arrow or?
Yeah.
You can see, that's fine. So you see these two lines which are meeting at a point. So that's why it is called as a point measurement. But similarly, laser source, if it is diffused or transformed in the form of a plane or a sheet, then essentially we are doing measurements in a plane, which is a 2D plane. So we call it as a PIV, particle image velocimetry, or PLIF, planar laser induced fluorescence. The similar laser, if it is thrown into the area of interest as a frustum of cone, as a spotlight, then essentially it is illuminating a volume in the region of flow. Then you can do some volumetric measurements. We call it as V3V, volumetric three-component velocimetry. So these are basic steps: point, plane, and volume. I'll just give you overview of all these three techniques so that you have some hangover of the actual technique, how it works. Let's come to the point measurement that we call it as an LDV or a PDPA. You can see this spray injections. There is a nozzle and you see some sprays. My core interest is to know at a junction point the velocity of the flow. Okay, and I may be also interested to know the droplet size of the fluid. In second image, you see there's an IC engine cutout. You understand IC engine being in mechanical. There's a cylinder, there's a piston. So with the help of crank, this piston reciprocates inside the cylinder. And I'm more interested to know what is the velocity at this particular point, measurement point, using some LDV technique. Okay, so when you're only interested to know what is velocity, we call it as a laser Doppler velocimetry. But if you're also interested to know what is the particle size of these droplets or droplet size in terms of diameters, then that is an extended version of LDV. We call it as phase Doppler particle analysis, PDPA. And essentially both are point measurement. So what I'm trying to introduce here is the laser light source intersected at a point. That is the key. There is no physical device going inside the flow, but two laser beams intersecting at a focal point. Remember that. How it works. From left-hand corner, there is one laser beam. I'm separating that laser beam into two parts. Then I have a spherical lens of a known focal length, and so that this both beams intersect at one point. So this circuit is called transmitter because it is transmitting the laser at a point of measurement. On the right hand side, you have another optics called receiver. So there are a pair of lenses which actually sees this point. Something is happening at this point has to be captured. So this guy is seeing this particular point when the particles are moving. And what it does is that it projects that whatever disturbances of something happening at the point at a photodetector. Photodetector is a sensor which converts the light energy or photons into electronics or volts or millivolts. Okay, so once you get the conversion of light signal to electronics, then you process the signal by using oscilloscope or any other signal processor and try to tell what are you essentially getting it. Our first aim is to get the velocity. Okay, remember that. Now, coming back to the real picture, these are some picture of a real laser beam which is meeting at a point. Now, if I chop the cross section of this meeting point, if I try to chop and see what it is, it looks like this, a green circle with some pattern. Can anyone tell what is this pattern all about? Fringes. And why does this fringe? Uh, because of? Yeah, great, great. So when the two lights collide with each other because of interferometric effect, this fringe pattern is formed. Good. So think that this is a playground, a neat, clean playground inside the flow. Okay. So now we have to play football or cricket or whatever. Some disturbance will happen in this playground, and you have to tap that disturbances and know what is the velocity. Primarily, we are trying to tap velocity. So in this picture, I am asking this small white dot, a particle, to cross over this playground. Is running. Okay, so from top to down, it is running, and in the right hand corner, I'm trying to tap the intensity signal in some oscilloscope. Now you understand the boundary is lighter compared to the center core, like a sun. The center core is more intense compared to the peripheral boundaries. So when the particle is entering the boundary, signals are low, but The moment it comes to the center core, intensity is increasing. And when it comes out, it again goes down. So you know that this is like a normal distribution or a Gaussian distribution, that intensity is increasing and then it is again reducing and forming a normal distribution. Now tell me why this signal is oscillating. See the right signal? You see that there is an oscillation in the intensity. Up and down, up and down, up and down in the intensity. Reciprocating nature. What could that be?
Maybe a motion of fluid or something.
No. Yes? Yes, absolutely, absolutely. Because fringe is a bundle of intensities with dark light patterns, right? तो intensity variations है. जैसे ही वो light portion में जाएगा, it will shoot up. When it comes to the dark portion, intensity falls down. Okay, so whatever oscillations you are seeing here in the signal is purely because of fringe pattern. Okay, so if you can know the frequency of this oscillation by some means, okay, now tell me what is velocity? Distance upon time? Okay, yeah, so distance upon time means what is the distance here? It's all written actually, but what is the distance here? Uh, uh, Wavelength, yes, yeah, wavelength upon the 2 sine kappa, it's written here. Wavelength is a laser wavelength. Kappa is an angle. What could be this angle? That is the angle of when these two laser beams are meeting at a point, there is some angle involved. You see this angle? Okay. So if you know this angle, if you know the wavelength, you can determine the fringe spacing. That is df. You know what are the number of fringes, what is the distance between the fringes. These are standard logged parameters depending upon the wavelength and the angle. Okay, so you know what is the spherical length you're using, what is the focal length, so you can evaluate what is the angle. You know which color light you are using or the laser you are using, say green color, so it is 532 nanometers. You know the wavelength. By this formula, you get the fringe spacing, or in terms of velocity, you get the distance. Now, where is the time parameter? Yeah. So time parameter is evaluated by knowing the frequency of this oscillating signal. Frequency, yeah.
But these fluctuations, these oscillations will be initiated when you are having exposed this thing to some fluid in motion flow.
Yeah.
So that was my take. No? I was telling you that
Yeah.
otherwise you won't be having such oscillations. So you are
Yeah.
just
Yeah.
catching these oscillations and then finally just getting velocity data from this.
Exactly. So there is a flow, and because of that flow, there is disturbance in the intensity.
If you don't have any this thing flow,
Yeah, then nothing will happen. Particle is important. You're right.
particle is important.
If it is a very clean water or clean air with zero particles, then this instrument is of no use.
Yeah.
You have to put some particle
Seeding,
inside the flow.
because that's called seeding.
That is called seeding. We have to seed it.
Okay.
But in a spray kind of thing, the droplets are natural seeders. Then you do not to seed. But in a normal water flow, we do seed with some hollow glass particle. In air, we do seed with some fog generator droplet. So we have to seed it. And this seeders or the particles should have some properties which is equivalent to the fluid property. Then only you can claim that this is the velocity of the flow. Otherwise, essentially you are measuring the velocity of that particle, not the flow. Okay, so beware. Like हवा के अंदर मैं sand डाल दूंगा और sand की velocity measure करूंगा, I cannot say that that is air velocity because sand is very heavy compared to air. I am essentially measuring sand velocity, If I want to know air velocity, I have to see with some particles which resembles in terms of density with air or water or whatever medium you are measuring in. Remember that. That is important. So, if we can know the fluctuation frequency, we call it as Doppler frequency. Frequency is 1 upon second multiplied by the distance, you get the velocity. Okay, so I wrote here ux means I'm measuring velocity in one direction because it's a 3D space. You can measure velocity in all three directions. But with given configuration, you can only measure velocity in one particular direction, 1D. What is that dominant direction? When these two light beams are meeting at a point, this is the dominant direction. Down. Okay. But so by this arrangement, I can measure, say, vertical velocity of the flow. If I want to know the horizontal velocity, what should I do? Change the orientation, right? So I can change the orientation by 90 degree, or I can introduce another laser at 90 degree. So I can use two different laser sources also. One is vertical, one is horizontal. So one creates vertical plane, another will create a horizontal plane. So I can use multiple lasers. If I use two lasers, that system is a 2D LDV or two component LDV system. I can use three lasers also. We call it as a three component velocimetry. Sorry. So the main part is now here that I want to know the frequency of this particular oscillating signal. So let's see this signal. I have taken this signal nicely, visualized in an oscilloscope. Okay, I am not interested in the intensity values, absolute values. What is the peak and what is the lowest value of the intensity? I am not interested in that. So what I will do is that I will find a average normal distribution of it and subtract it. We call it in electronics as high pass filter because I'm not interested in the intensity values. So I have found out what is the average intensity and subtracted, moving average. So now I'm left with a pure fluctuating signal. And I see initially there is some noise, and here also I see some noise. So I will again apply some low pass filter to clear the noise. And after that, I see a very clean fluctuating signal. Okay. Now I want to know the frequency of this signal. How to find that? Anything come across in your mind? From a stamp of a oscillating signal, how can we determine the frequency value? Any technique you have come across, have read somewhere, especially MTech guys or PhD guys who are doing some computing? Any word which can convert this into frequency? Okay, so essentially that word is called FFT, fast Fourier transformation. Okay, so you have to apply that fast Fourier transformation to get one particular dominant frequency for this particular signal. There can be n number of signals, so there can be n number of values of dominant frequency. Currently, we are just working with one signal because there was only one particle. There can be tens of particles going from that point, small point. So there could be tens of signals. So your processor should be strong enough to identify each and every signals and then give you frequencies. Okay, all particles will have their own frequencies, right? If they're identical and moving with same speed, then their values will be similar. But in a turbulent flow, you can't expect that. The values will differ a lot. Within that small circle, within that small playground also, all players are moving here and there with different velocities. So that is the beauty of this technique that you can tap each and every signals and get the feel of velocity, which is time dependent. So that is all about velocity. Now you should have curiosity that yes, now I was also telling that how can we tap the size of those particles or droplets by laser? Velocity was clear. I know fringe spacing, and I know the spacing. I know I can timestamp the frequency. Then I multiply it. I get the velocity. And the best part of LDV is that you don't need a calibration. This works directly on the first principle of physics. You don't need a calibration. If you use any manometer in your lab, digital, it needs to be calibrated. Hot wire needs to be calibrated. This is the only device which gives you direct reading without any calibration. Because whatever frequency you have measured is actual, and whatever spacing you have derived for the fringes is also actual. No calibration required. Now sizing. Same point, same particle moving in the fringe, but I want to now observe this particle with a big receiver. I have a big lens where I have mounted three sensors, A, B, and C. And all the sensors are essentially watching this particle when they are crossing. And now, here what are we trying to measure? Fringes and all is fine. That is velocity. और क्या हो सकता है जब particles अगर point को cross करेंगे, what else you can see apart from fringe and all? Scattering, yes. जैसे ही particle cross करेगा, there is some scattering. That is the catch. And this scattering is proportional to the size of particle. Okay? Smaller the size, larger is the scattering, and larger the size, smaller is the scattering. It's like solar eclipse, what you see and all. Okay? So I'm trying to see this scattering from three different zones because scattering is a qualitative phenomena. It's a visual. How to quantify it? I need some references. Okay, that's why I'm using three zones, A, B, and C, which are deliberately spaced with some phase differences. And I'm trying to tap the signal and trying to gauge how I can correlate that with a size of particle. Okay, otherwise scattering is just a qualitative phenomenon. I got the scattering. But what am I going to get from that intensity scattering? Millivolts? How millivolts can be converted into diameter? Not directly. So I'm trying to see the same scattering at from three different phases and trying to figure out what is the phase difference and then assign a value of diameter to a particular phase difference. So here a calibration is required. Now, where to keep this receiver? Where to keep this receiver? स्कैटरिंग तो मुझे देखना है कहाँ से ज़्यादा अच्छा दिखेगा सामने से साइड से कोई एंगल से सो देयर इज अ थियरी बिहाइंड इट या आप पीछे से देखेंगे आप तो कुछ दिखेगा क्या सो टू अंडरस्टैंड दैट यस let's try to see one droplet. This is a spherical droplet, transparent droplet. Okay, so laser beams are these are the incident beams which are hitting at the surface of the droplet. After hitting, it reflects backside. But this being transparent, it will also reflect inside. It goes inside. And then again it hits to another wall of the bubble. From here, it will again reflect internally, comes here and goes out as a rainbow angle or prism angle with your spectrum, what you know about. But it will also reflect out of this wall, and you can see some reflected light here. So if this is the center, the right hand side is called forward scatter and the left hand side is called backward scatter. So मुझे रिसीवर कहाँ रखना चाहिए अगर मुझे स्कैटरिंग सिग्नल देखना है तो ideally where should I keep the receiver? Any idea? Yeah, I should keep the receiver here in the right hand side at some angle, say 20 degree or 30 degree, because this area is receiving the reflected signals of the scattering. If I keep it here, there's no signal. If I keep it here, I will see a signal, but it's a rainbow, a whip cure, which is of no use to me. I can also keep it here because it is also reflecting. Okay, so here I can get the diameter from a forward scatter placement of the receiver or a backward scatter placement of the receiver. Instead of this transparent bubble, अगर मैं एक sand particle लूंगा, what will happen? Yeah, instead of a transparent bubble, if I use sand, which is opaque, what will happen to the scattering signal? सारे signals backscatter में होंगे, backside. Okay, so for that receiver has to be kept on the back end side at some angle. Then only you will get the scattering signal. Front side में कुछ नहीं दिखेगा because it is an opaque device, solid sand particle. So depending upon the seeding particle or the particles you are interested in, you have to keep the receiver. Backscatter is good for all. You'll always get signals in backscatter. So receiver has to be kept in that fashion. And then, as I said, we have three detectors. I'll get signal from A, B, and C. I will try to figure out what is the phase difference between AB and AC, and I will try to figure out what are the slopes of AB and AC, and then with three detector approach, by a redundant test, I can come out with a value of a diameter for a given intense laser beam and the condition. So in factory, what we do is that we use known size particles. We know what is the size of the particles. We will deliberately put it in the point of intersection, allow it to flow, and calibrate the receiver with a known value. Now I know the signals of phase differences, then I assign that calibration constant to get the diameter. So when you use a receiver, that particular receiver has its own constants for AB and AC, for phases. And with any unknown diameters can be measured. It's factory calibrated. So for LTV, you don't need a calibration. For PDPA, you need a receiver, which is pre-calibrated. Got it? And of course, these receivers are also seeing the fringes. A, B, C, तीनों sensors fringe pattern भी देख रहे हैं. So velocity is a natural byproduct to PDPA receiver also. So if you take a PDPA receiver, velocity and sizing both are acquired together for a given movement of a particle. But with LTV, no sizing. It's purely velocity. So these are how the system looks. This is the box which will allow the laser to transmit. This is the receiver and so on. Anyway, these are all hardware, so I won't talk much about hardware. My interest is to know the technique. And these are some examples. You can see the ICE engine, bike का engine होगा ये, जहाँ पे spark plug connect करते हैं. And this is the probe. I'm more interested to know what's the tumble velocity at different crank position. So you know crank moves with multiple rotations and you know how the velocity is moving. Swirl velocity, tumbler velocity. You can also know for combustion diesel injectors are used where air fuel mixtures are done, or you can know at the tip what's happening. You can use in some combustors. So these are some examples I'm trying to say for PDPA. Like this is a spray. I can, so essentially your cross point should move at different locations if you need information around the complete jet or a spray. एक जगह पे रखोगे तो आपको local value ही मिलेगी. You need to move it. So what we do is that we mount this transmitter or the probe on a traverse mechanism, which is automated or controlled through software. And I will give XYZ location वो पॉइंट एक जगह पे जाएगा, मेजरमेंट ले लेगा, इट विल गो टू द डिफरेंट लोकेशन, एंड so on I can map what are the points of my interest within the given flow. Like this. यहाँ से सामने से एक jet आ रहा है, vertical actually coming out, and there are two probes which are measuring. Why there are two probes? Because one probe, they are accommodating three velocities, 3D. So one will have two lasers and another will have one more laser. So there are three lasers intersecting here. You can determine the turbulence characteristics. You can use in high-speed flow, and so on. So this is all about point measurement. Any questions?
Yes, sir. So, bit loud. Ask you one.
Yeah, tell me.
Good morning, sir.
Yeah, good morning.
Sir, am I audible, sir?
Yeah.
I just want to know about these point measure techniques you mentioned in the first part of the
Yeah.
Sir, what about this when there is turbulence, when there is knocking, sir, in engine, sir? At that time, is this equipment fully reliable?
Knocking in the sense the flow is turbulent, right?
Obviously, it goes turbulent. Flow becomes turbulent, and we don't have a proper flame propagation, and this will be in this combustion cycle.
Yeah. So essentially, this probe or the system should not be directly connected to that knocking or vibrating devices. This is kept separate. Okay. I don't want this point to be affected by the knocking of the flow or the disturbance of the flow.
But we don't know actually, sir, where the knocking was going to happen because
That is good. Actually, this help. This will tap you the frequency of that knocking. This device will give you direct frequency of that knocking.
so will it be reliable to use in that case?
Yes, definitely. People use it left and right for that to measure disturbances also. If there is some disturbances in the flow with some known frequencies, this is the actual device which gives you the dominant frequency. It measures Doppler frequency.
Okay.
Okay, like hot wires. लेकिन हॉट वायर का टूटने का डर रहेगा, इसमें ऐसा कुछ है ही नहीं. It's just a beam. But the limitation is particles should be there. Hot wire runs in a clean flow, while LDV runs in a seeded flow. Okay, and this device needs an optical axis. मतलब जाना चाहिए जहाँ पे आपको मेजरमेंट करना है, उस जगह पे लाइट्स जानी चाहिए. अगर अगर स्टील पाइप है या क्लोज एनक्लोजर है जहाँ कुछ दिखता ही नहीं है तो ये जाएगा भी नहीं. So you need to provide optical access window for this beam to go inside and do the measurement. Any other questions?
Please go ahead.
Yeah. Now we will go with two component measurements or the planar measurements. We call it as PIV. Again, the logic remains the same. Instead of point, you are measuring in a plane. Flow should be seeded. There should be particles inside this. That's why it is called particle image velocimetry and not the flow image velocimetry. We are only interested to know the particle velocity. If that particle resembles the flow, yes, then it's a flow velocity. Or whatever that particle resembles, that is the velocity of that. So, how it is done? Technique is different in a way that this use cameras. Now you are looking at a wider field. The laser beam is converted into some sheet which is illuminating the region, and you are looking by the camera. Those particles are visualized by the camera. Okay. So I have a laser light sheet, and there are particles. These are black dots. I say particles in it. I'm trying to see at one particular region how the particles are looking, and after a certain time how this particle is visually looking or how it gets displaced. So now just imagine you take one image. In that image, say you're taking an image of a particle. या आप किसी का फोटो ले रहे हो, जो एक कोई लड़का लड़की, आपने एक फोटो ले लिया, अकेला खड़ा है वो, एक इमेज ले लिया, एंड आफ्टर फ्यू सेकंड्स अगेन यू आर टेकिंग द इमेज ऑफ द सेम गाय हु हैज मूव्ड अ बिट, थोड़ा हिल गया, आप फोटोग्राफी फास्ट नहीं कर रहे हो, वो इरिटेट हो गया और वो मूव हो गया, but second picture shows the displacement. First picture you have the exact location, second picture there's a displacement of that particle or a person. Okay, so I by realizing both the image you can know what is the displacement made by that person or the particle in between the two images. तो मुझे पता पड़ जाएगा इतना डेल्टा एक्स है, इतना डेल्टा वाई, ये बंदा या बंदी मूव हो गई या पार्टिकल मूव हो गया, एंड मैंने इतना टाइम लिया दोनों इमेज के बीच में, डेल्टा टी. So I know delta x or I know delta y, and I know the time given between the two frames or the two images, that's delta t. So delta x by delta t is again velocity, delta y by delta t is also velocity. So straightforward, I will get two component of velocity in x direction and y direction, say u and v, delta u and delta v, whatever you call it. Okay. So now question is, with this system, what is the essential part is delta t. How quickly or how much time you are taking to take the second image. आपने ज्यादा टाइम लगाया तो वो पार्टिकल भाग जाएगा, वो पर्सन भाग जाएगा, नहीं यार नहीं खड़ा रहना, it's too boring to stand in front of this photographer, he is not clicking in time, taking too much of time, he runs away. Then आपका second image blank है, then you cannot determine the velocity. But हो सकता है second image blank तो नहीं है, वो बंदा तो निकल गया लेकिन और चार लोग आ गए, because it's a flow, there are hundreds and thousands of particles in it. Then system can get confused. अरे मैं एक का पिक्चर दे रहा था और मुझे पांच पांच नजर आ रहे हैं सेकंड फ्रेम में. What's happening in this particular flow or plane? So we do refine the algorithms. We do statistical analysis and algorithms to figure out the part, because all particles look same. It's a bunch of stars shining in sky. Okay, you cannot distinguish between each and every particles, but you are trying to map the behavior of a group of particles by taking small interrogation area. हम छोटे छोटे boxes लेते हैं, उनको सिर्फ review करते हैं between delta t. How does it move? As a full image, I may not get a feel, but small boxes can give me an idea. एक बॉक्स में है चार पार्टिकल, आफ्टर डेल्टा टी ओके चार है, that's okay, that's fine, that is a good enough size, and then with the help of delta t I will evaluate the complete frame of the camera or the image. So we take frame 1, we take frame 2, we see a small interrogation area, we correlate with the second image and replace this interrogation with a vector. We do a cross correlation between these two boxes, small boxes, and replace that with a vector. And then I will bring this region and cover the entire frame. And then I will have multiple vectors, and that constitutes the flow field. And that's how a PIV works. So any query in this, because this is the crux of PIV. Let me know right now. अगर कोई डाउट है, कोई क्वेश्चन है. Oh, so we are seeing the displacement of these particles or a bunch of particles in the time delta t, and then mapping it in form of vectors. So these are some examples I can show. This is an aerofoil, and I'm trying to understand the wake profile behind the aerofoil flow in a wind tunnel. These experiments were done in my own lab at IIT Kanpur, so I have some good images of that. So you know what is a wake profile? When there is no separation, yeah, you have a very low velocity, and this is free stream velocity, the red zones, or higher velocity, you may say. This is the same profile. This is a big wind tunnel. I don't know if you might have visited IIT Kanpur, you can walk inside this tunnel. And this is the aerofoil blade which is kept, and PIV is done at the back side. And this is the complete weight profile captured from PIV. These are again some, I'm from aerospace, so my all images will be from, in the aerodynamic perspective, air, not much in water. So this is an aerofoil, and this is a laser sheet. You can see the camera image. I'm more interested to see what's happening here. A different angle of attack for this aerofoil. These are all PIV images. At some angle, there is no separation, and then if I change the angles, there are some separated flows I'm seeing. This is flow past a cylinder. I'm more interested to see what is the flow here in this region. These are all behind. This is all PIV data. A different Reynolds number of flow rate. And if you have understood what is flow past a cylinder, you might see some vorticity structures clockwise and anti-clockwise, which can be determined by using PIVs and how they are advancing or growing with respect to Reynolds number. Some stresses, Reynolds stresses. Yeah. You can also have some streamlined profiles of the vorticities, structural movement. Some more examples. Yeah. So this is about PIV. By using PIV technique, you can also do some spray analysis. Like there is some spray and cameras are capped. Now everything will be more of visual. I can know what is the cone angle of the spray. I can know what is the, of course, velocity, diameter. Diameter also I can define. I'm not using LDV, through imaging. So I can know how this spray gets evolved. I can also know the sector patternation of the spray. I can also know the sizing of the spray droplets by using image. While PDPA is point measurement, no imaging. At a point with PIV, you can know it by image itself. If you have an image, you can also know. There is also interferometric technique involved. This is the principle of interferometric. Fringe patterns are created in the image itself. These are all fringes. And from the fringe spacing, I'm determining the diameter of the droplets. So from imaging also you can do it. And these are all plotting of the data. You can use similar technique for combustion flames, for doing some scalar quantity like temperature distributions or concentration distributions and so on. So I may skip the technique of LIF, that's okay. Yeah. So this we recently did, recently when COVID was in full form, we wanted to know when you wear an N95 mask, then is there any leakage inside going to your nose and all by using a PIV? So we used a mannequin with some flow duct. This video can help you to see that. So this mannequin is without mask. Then we'll put some mask and do the same measurements. It is kept in a box, and in that box we are seeding some smoke. So there is a seeder here in the left corner, and this white is the camera and the laser sheet. So this is the seeder, and there is a pipe. ये पूरे बॉक्स को smoke से भर देगा, and now this light is going, and this mannequin is breathing that I've kept a nozzle here, which replicates that person is breathing. So this is the PIV of the same thing. So air intake was from the mouthpiece kept here. So you see that all flow leads to the mouthpiece. Now we have put the same thing with the mask. These are all seed particles, what you see here. So PIV can also be used for flow visualization naturally. And now these are the quantified PIV results, the vectors. So we figured out from the nose end, there's a leakage. Obviously, जब आप mask पहन रहे थे तो आप नाक पे loose रखते थे because it was not helping you to breathe. The moment you keep it loose, air will go inside. So that's how some experiments were done. Now I'll quickly brief volumetric PIV. PIV was using one camera. Now I will use multiple cameras, 3 or 4, to determine the volume. Similar PIV concept, but by using 3 cameras and looking at a volume region. So this is a raw data, bunch of particles, and this is the processed data. This can be arranged in different fashions. The cameras, ये कुछ live pictures and how the cameras are arranged to see the volumes. And here we determine interrogation volume. We have delta T and everything. It's in line with PIV, but observed with 3 or 4 cameras, and data are stitched to determine XYZ, PUVW in one go. Like this is a jellyfish. I don't know whether this video works. So this jellyfish is moving up, creating a wake. So this is the wake profile. Jellyfish has gone up, but behind you see some wake profiles are left behind. These are all structures, vertical structures in a flow, which people do determine using CFDs and all. This is purely experimental. Again, there are some experiments done on droplets. This is droplets, and it is in air, and I'm also seeding the air with some fog. So I want to know the behavior of the droplet as well as fog, both multi-phase or two-phase. So this is the picture where all these things are particles in air, and these dark ones are droplets of water. So I can identify the droplets of water, I can know the size of water droplets, and from the other part, I can also know the vectors of the air, or the particles in the air. So this is the processed image. You can see the water droplets coming, and all of a sudden a big water droplet came in air motion. Yeah, so those are live pictures. I don't know whether this is working or not. Yeah, and then you can do multiple experiments and all. Yeah, so I think this is fair enough for today. Before you go for no, today's Ramzan has started, or yeah, okay. In Bangalore, it's from today. They had started yesterday or from today? Hey, but in Bangalore, it's from today. So yeah, so, so you have to skip your lunch. Anyways, yeah. Let me. Any questions? Let me see. Yeah.
Sir, I have a question. Sir, you actually already said that you have used on air. So
Yeah.
most of us are working with fluids. Sir, liquids.
That is okay. Liquids are still better compared to air because that is more controlled in a chamber or in a tank or in a pipe or somewhere. Air is something it is uncontrolled, difficult to control compared to water. Water is all good enough. Only you should provide an optical access.
So we don't need seeding. For example, we are using nano powder nanoparticles hit, were forming
Uh,
voluminous nanofluids.
I don't
वाटर
think
के
so.
अंदर नेचुरल impurities होती है, but I would recommend that use some seed particles.
Seed particles.
Even in case of nanofluids.
Uh, no, because see, the laser wavelength is around 500 nanometers. So you cannot measure anything with PIV or LDV below 500 nanometers or zero point 0.5 microns.
So Mark Zimmer is being used for that. So how
Yeah,
they are being
for
used?
nanoparticles, you cannot use imaging. There are other ways to determine nanoparticles. Zero point 0.5 and above is good enough. Zero point 0.5 microns and above is good enough for this techniques, laser-based techniques, because of the laser wavelength. I can change the laser wavelength. मैं 200 nanometers का भी laser use कर सकता हूँ, but that is UV, non-visible. वो visible ही नहीं है तो आगे process ही नहीं होगा. Here we work more on the visibility of the light source.
Anyone else? आप लोग आगे.
So the cost of equipment, for example, if you want to buy PIV for the lab, how much will it cost?
See, it all depends on the configuration we want to set. कैमरा कैसा चाहिए, लेजर किस स्पीड का चाहिए, कैमरा कौन सी स्पीड का होना चाहिए. So technically ये this can go from, I can say, in current scenario, from 50 lakhs to 3 crores. So what configuration will suit to your application. आप लो स्पीड के लिए बना रहे हो, सोच रहे हो मैं सुपरसोनिक में यूज करूंगा तो वो होगा नहीं. तो supersonic में high speed lasers, high speed cameras, and those are super expensive. The laser itself is 1 crore plus. But एक lab scale पे आपको low speed के लिए बनाना है, that can be done in 30, 40 lakhs, 50 lakhs of kind of figure I can tell.
Anyone else? Danish.
So it's an expensive device.
Ah, it's very expensive.
Pitot अच्छा है. हम ले
Pitot
लेंगे
tube is
100
good for
200
us.
रुपए में बना देंगे.
For NIT people, it is good. Pitot tube is good.
So everywhere and yeah, Pitot tube is a good device, as I said, for average velocities. It's all good.
But for field limits, it might.
But if you need to go in the
Field.
micro level of fluid diagnosis, then yes, you need hot wire. So सबसे cheaper है pitot tube, venturimeters and all, then hot wire, and then comes LDV, then comes PIV and so on.
So anyone else? Okay. Dr. Deepak Sharma. Thank you.
Yeah,
Just,
yeah. Thanks a
just,
lot.
just a moment. We have a momentum for also for the session. So
क्या बात है, virtually लेना पड़ेगा.
virtually भी आप ले लो. You got the moment. चलो. चलो.
Thanks.
So thank you. So we are looking forward next time. Maybe you'll be here with us.
Yeah, I would have loved to be there in front of everyone and enjoyed the melting of snow with some clothes.
Next
But
time.
some other time I'll make it.
Definitely invite you here.
Yeah,
For this
thank
class.
you.
Chalo, thank you.
Yeah, have a good day
Okay,
and a
bye-bye.
great festival around.
Okay,
Yeah,
fine. Bye.
bye.
And I suppose. So, question.
Good afternoon. Welcome back. Last but not least, we have Dr. H.S. Pali, who will be discussing outcome-based education. Dr. Pali is an experienced professor and has been involved in designing and implementing outcome-based education programs. I now request Dr. Pali to come here and take over the desk.
So good afternoon to all. Please come forward so that we can decrease the distances between the student and the teacher, or you can say your today's resource person. Please come. So there is no need to mic. I'm audible. Please come forward. Okay. So the topic is the outcome-based education. You heard about it? सभी ने सुना है? Currently, we are focusing from last to last decade. We are more focused about the outcome-based education. What is the difference between the previous education policy and the outcome-based education? Anyone know? What is the difference?
But actually, there was a research which stated that if the student, instead of going through the your lectures first, if he first practices the questions and then goes to the lecture, it becomes a little bit inefficient because the student he has the idea of what he's going to get out of this whatever he's studying. So instead of first attending the lectures and then looking into what he has learned, we are first describing all the things that he should learn from this topic and then he start learning.
Very good. It's partially true, and this is the main objective of the outcome-based education. However, another issue is there. Yes. More flexibility about the new education policy. It is not an Indian context; it is a global phenomenon. The main difference. So initially, from the start of the engineering education, the education is based on the teacher centric. Education is the based on the faculty centric. If the faculty is more experienced, has a good competency and good knowledge, then we can say it is a good institution. But last 10 or 15 years back, when Washington Accord decided in 2014, the education should be on the student centric. Means इस बात से कोई अंतर नहीं पड़ता कि फैकल्टी कितना क्वालिफाइड है, अंतर किस बात से पड़ता है कि स्टूडेंट को क्या आता है, जो हमारा ग्रेजुएट तैयार हो रहा है उसकी क्या कॉम्पिटेंस है, व्हाट इज द एबिलिटी हैज द स्टूडेंट. It does not depend upon the faculty competence. So this is the main objective of the outcome based education. Outcome based education, we want to know what is the student is the industry ready. He exactly know what is the meaning of the basic laws of the sciences or engineering. So very simple example से start करते हैं. For example, आपको बाइसिकल या बाइक या कार चलाना सीखना है, ठीक है? तो एक वेरी गुड प्रेजेंटेशन तैयार किया जाए जिसमें बताया जाए व्हाट इज द मेन कंपोनेंट ऑफ द कार, what is the functions of the individual brake, steering, clutch system, gear system, and all good presentations and good deliberations on the learning of the teaching of the to drive a car. You are able to drive the car after that lecture or after that semester. What is the life? However, you can write the very good question paper answer of that teaching. जो आपको पढ़ाया गया है उसके बेसिस पे आपसे क्वेश्चन पूछा गया है व्हाट इज द हाउ टू व्हाट इज द मेन थिंग्स और मेन एट्रीब्यूट्स ऑफ द गुड ड्राइवर यू मे राइट एवरीवन बट ये पॉसिबल है कि आप कार चलाना सीखे हो क्या लैक है स्किल नहीं है that is related to the skill that is not related to the knowledge so two things are there one is the knowledge knowledge not fundamental knowledge or understanding of the subject the knowledge regarding the you can say it is the cognitive knowledge or knowledge for the critical thinking and that transform into the skill वो नॉलेज किस में कन्वर्ट होना चाहिए स्किल सो द मेन ऑब्जेक्टिव ऑफ द आउटकम एजुकेशन टू ट्रांसफॉर्मेशन ऑफ दिस कॉग्निटिव नॉलेज इनटू द स्किल कॉम्पिटेंस यू आर गेटिंग पहले हमें टॉपिक क्यों आज के लेक्चर बैठ के क्यों सुन रहे हैं ये मालूम होना चाहिए व्हाट इज द एसेंस ऑफ दिस लेक्चर सो दिस इज द मेन ऑब्जेक्टिव आपको यदि सिखाया जाएगा देन धीरे धीरे 15 दिन में 1 महीने में आप कार चलाना सीख लेंगे देन यू विल गो ऑन द आरटीओ ऑफिस यू विल टेस्ट यू हैव द बेसिक skill of this car driving then they will provide the learner certificate या डायरेक्टली सर्टिफिकेट वो दे देते हैं आपको ड्राइविंग लाइसेंस क्या देते हैं पहले लर्नर ड्राइविंग सर्टिफिकेट व्हाट इज द रीजन बिहाइंड दैट क्यों नहीं दे दिया डायरेक्टली जबकि उसको तो चेक कर लिया था आपको कार चलानी आती है experience what is the meaning what is the need of the experience in that case yes so we want to achieve the higher level of that skill we want to achieve the higher level of skill that is known as the lifelong learning that is known as the lifelong learning if we understand after 6 months if we drive the car then we are able to perfectly we can drive in every situation and after the 6 months they will provide the final driving license that is the advanced level of the learning and after receiving that driving license you can leave this driving and after 10 year 20 year again you want to drive you are able to drive or not आपने साइकिल बाइसिकल या कार चलाना सीखा एक बार और फिर आपने छोड़ दिया 10 साल तक फिर उसके बाद चला पाएंगे या नहीं चला पाएंगे बस थोड़ा सा प्रैक्टिस की जरूरत होगी दोबारा यू कैन कैरी दिस थिंग सो दिस इज द नोन एज द लाइफ लॉन्ग लर्निंग सो मेन फोकस ऑफ द आउटकम बेस्ड एजुकेशन first we have to understand the cognitive knowledge and then transform into the skill and then after we want to convert into the lifelong learning or psychomotor इसका एक और बेटर एग्जांपल बताता हूँ जो लोग कार या ड्राइव करना जानते हैं फॉर एग्जांपल लाल चौक पे या लाल बाजार में आपका घर है और आपने कार स्टार्ट की सुबह कॉलेज जाना है आपको स्टार्ट की उसके बाद किसी का फोन आ गया तो आपने फोन अटेंड किया और कार चलाते हुए कॉलेज में आ गए तब ये ध्यान दिया कि कहाँ मोड़ लिया कहाँ पे आपने ब्रेक लगाया कहाँ पे हॉर्न दिया ऐसा होता है दिमाग कहाँ पे था आपका फोन पे बात करने में पर कार चलाते हुए कॉलेज में आ गए व्हाट इज द मीनिंग yes it is the known as the lifelong learning or psychomotor means final stage after that you can understand there is no need to recognize the what is the अब कोई आदमी सामने आ गया है हमें ब्रेक लगाना है ऐसा कुछ ध्यान रखने की जरूरत नहीं या टर्न आ रहा है मोड़ने की जरूरत नहीं बट शुरू के 6 मंथ में ऐसा था जब आप लर्निंग सीख रहे थे तो था सो दिस इज द मेन एसेंस ऑफ द आउटकम बेस्ड एजुकेशन और लर्निंग if you are able to learn these things then objective of the outcome learning will be fulfilled so the main topics what is the OBE अभी जो हमने डिस्कस किया उसके रिगार्डिंग, एंड व्हाट आर द की टर्मिनोलॉजी, because when you are roaming here and there, you can see number of boards are there. Somewhere is written vision of the institute, mission of the institute, program educational objectives, program outcomes. देखा ना, कहीं 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 भी देख रहे कॉलेज में घूम रहे हैं, सब जगह लगा हुआ है, बट उसका मतलब मालूम नहीं है किसी को। तो मेन ऑब्जेक्टिव क्या है जो टॉप का है कि ये अब जब आप घूमना स्टार्ट करें तो आपको सभी को मालूम हो कि व्हाट इज द मीनिंग ऑफ दिस। सो द की टर्मिनोलॉजीज क्या क्या हैं उसके रिस्पेक्ट में, एंड व्हाट इज द फ्रेमवर्क हाउ टू इम्प्लीमेंट। करंटली जो टीचिंग लर्निंग प्रोसेस है वो हमें सबको मालूम है कि हमारा किस तरह से आर्किटेक्चर है, बट वी वांट टू शिफ्ट दिस टीचिंग लर्निंग प्रोसेस और टीचिंग सेंट्रिक एजुकेशन इनटू द स्टूडेंट सेंट्रिक एजुकेशन। देयर इज द certain framework is required, then after the administrative क्या है उसका concept as well as why we need this outcome based education and why we are emphasizing the outcome based education. So these are the main things. Main we have discussed two things. Another thing is according to designing both curricula and delivery mechanism. How can develop these skills? Obviously, we have to design the curriculum. Curriculum and syllabus two terminologies are there. You can differentiate both the things. What is the difference between the syllabus and curriculum? Syllabus is the written format and that is the related to the cognitive knowledge. And curriculum is the extracurricular, different type of activities that is performed in the whole or overall development of the engineers. So it is related to the जो FDP आपका हो रहा है, that is the one of the part of the curriculum. कि आपको ये क्लासरूम टीचिंग में ये पता नहीं लगता ये सारी चीजें। कुछ चीजें ऐसी भी हैं जो हमें एक्स्ट्रा गेम्स के दौरान, FDP के दौरान या फिर डिफरेंट डिफरेंट एक्टिविटी करने के बाद पता लगता है। You are getting? So we have to design the delivery mechanism. Delivery mechanism is not only the lecture based, it should be based on the activity based learning or practical based learning. Practical based learning, in the labs we have to perform some experiment. We can devise an activity to learn any phenomena of the basic science. So this is the requirement. Another important objective is the students are more employable. If we know the something about the engineering, about the skills or competency, then the job is in the industry. It is very easy. At the end, we generally go for the internship and all the things. We want to learn some training-based program. So, what is the meaning? Meaning is we want to convert this knowledge into the competence or skills. And finally, what is the purpose of the institute? Institute purpose is that we want to accreditation from the recognized agencies. What is the meaning? आपने इस तरह का ऑब्जर्वेशन लास्ट 2011-12 में आया हमारे यहाँ आईटी श्रीनगर के कुछ इंजीनियर्स जो यूएई में या फिर दुबई में काम कर रहे थे उन्हें वापस भेज दिया। रीजन बिहाइंड दैट ऐसा नहीं था कि उन्होंने इंजीनियरिंग की थी, बहुत अच्छे कॉम्पिटेंस था उनके पास, बट accreditation is the another parameter. So one agency throughout the globe, all over world, one agency is there, Washington Accord. So Washington Accord
दोनों साइड से आगे
दोनों साइड से आगे
होम पे चले जाइए, होम पे चले
OPS
is moving forward in the both the cases.
or one agency, if we achieve the degree from institute which has the accredited, and accreditation in India, every country have the own accreditation body. In India is the National Board of Accreditation, NBA. So if our degree is recognized by NBA, it is recognized by throughout the all these countries, all 30 countries, all major countries are there. US, UK are also there. You can see the United States and UK, Russia, all countries are signatories of this outcome-based education. If we are applying the outcome-based education on the basis of this assessment of the outcome-based education, these governing bodies or these bodies give the accreditation. So you are getting what is the need. आपके पॉइंट ऑफ व्यू से मतलब स्टूडेंट के पॉइंट ऑफ व्यू से क्या है, दे हैव द कॉम्पिटेंस, दे हैव द स्किल्स, एंड इंस्टीट्यूट के पॉइंट ऑफ व्यू से क्या है, इफ द डिग्री इज रिकॉग्नाइज्ड फ्रॉम द एनबीए, बोथ main objective is outcome based education. Okay, so after that, it is the definition of outcome based education. As per the Tucker, it is the first chairman of this Washington Accord Association है, उसका फर्स्ट चेयरमैन था. इसने बताया आउटकम बेस्ड एजुकेशन इज द प्रोसेस इन्वॉल्विंग द रीस्ट्रक्चरिंग द करिकुलम, assessment and reporting practices in the education to reflect the achievements of higher order of learning. Higher order of learning, जो मैंने आपको एग्जांपल दिया था कि आपको ध्यान दिमाग का यूज करने की जरूरत ही खत्म हो जाती है. हायर, क्या आपको मालूम है कि जो आपने देखा होगा ना, बेल्डर है या फिर हैमर चलाने वाला जो मिस्त्री है, उसे इधर उधर बात भी करता रहता है, हथौड़ा मारता है, हथौड़ा जाके लगता रहा है. और आप कोशिश करो पूरी कंसंट्रेशन के साथ भी तो लगा सकते हो जहां पे. तो ये that is the higher order of learning. Okay, so this is the one objective. Another is the mastery. Mastery means if you dismantle the thing and you can assemble. इंजन को खोल दिया और उसके बाद असेंबल कर दिया, और असेंबल करने में ध्यान नहीं रखा कि कौन सा पार्ट पहले लगना है कौन सा बाद में लगना है. ये कैसे इससे डेवलप होगी? when you know the exact or actual competence. So by the outcome based accreditation, the globalization has the brought a clear shift from the education as transmission of expert knowledge to education building the learner competencies or skills, including the learning to learn the lifelong learning. और फाइनली ऐसा बना देना जिससे कि आपको वो चीज, आपसे क्वेश्चन आपसे पूछा जाए व्हाट इज द फर्स्ट लॉ ऑफ थर्मोडायनेमिक्स, तो आपने याद किया है तो भूल गए होंगे. व्हेन यू अप्लाई दिस, तो आपको याद रखने की जरूरत नहीं है, कभी भी पूछा जाए, सोते जाते हैं किसी टाइम भी, तो आप बता सकते हैं. जनरली फिजिक्स में लॉज ऑफ मैकेनिक्स पढ़ा है ना, तो फर्स्ट लॉ सेकंड लॉ आपने लर्न कर रखा है और थर्ड लॉ ऑफ मोशन अप्लाई करा हुआ है, कहीं ना कहीं हुआ हुआ, किसी को या तो चाटा मारा हुआ है, किसी से खाया हुआ है, तो मालूम है ना एक्शन इक्वल्स टू रिएक्शन, वो याद रखने की जरूरत नहीं है। फर्स्ट लॉ यदि डिफाइन करना है देन यू हैव टू लर्न, क्योंकि आपने लर्न किया है अप्लाई नहीं किया है, दैट इज द इशू। एक्शन इक्वल्स टू रिएक्शन याद रखने की जरूरत है, बिकॉज दैट इज द, जब आपने उसे अप्लाई करके देख लिया, एक बार समझ गए एक्शन इक्वल्स टू रिएक्शन, तो कभी जिसने साइंस नहीं भी पढ़ा है वो भी बताएगा हाँ ये फिजिक्स का लॉ है, एक्शन इक्वल्स टू रिएक्शन। Clear? So this is the one important thing. Another thing, to understanding the fundamental very well, कोई भी चीज ऐसा नहीं है कि आपने सिलेबस का पार्ट है, उससे पहले डेफिनेशन था, उस डेफिनेशन में प्रकरण ने बहुत क्लियरली बताया है, ये लास्ट लाइन पढ़ सकते हैं, हमारा ऑब्जेक्टिव क्या है, लास्ट लाइन रह गया है, लास्ट में एक्यूमुलेशन ऑफ द कोर्स क्रेडिट। So you have to shift the paradigm, आउटकम बेस्ड एजुकेशन में क्रेडिट से कोई लेना देना नहीं है। आप हो सकता है कि आपके 60% क्रेडिट आए हो और आउटकम बेस्ड लर्निंग के अकॉर्डिंग आपका जो कॉम्पिटेंस लेवल हो ज्यादा बेटर हो, जिसके 10 क्रेडिट आए। So the assessment is the different, quite different। एनबीए का असेसमेंट उस तरह से नहीं है जैसे आपने जो क्रेडिट स्कोर किया है। तो कभी कभी क्या होता है कि कुछ लोगों का रिजल्ट बहुत अच्छा है और एनबीए के पॉइंट ऑफ व्यू से दे विल नॉट क्वालिफाई। Same happened in our institute. We have applied in the 5 departments. Only 2 departments are accredited because there are the certain criteria, certain levels. They have to understand what is the competency in that student, and if the competency is there, then they will provide the accreditation. So these are the terminology which is used in the outcome based education. Vision, mission, program educational objectives, program outcomes, or respective other things, the academic support units, and what are the techniques and framework we are using in the NBA. So we will discuss vision statements everywhere. It is disseminated throughout the campus. जहाँ भी जाते हैं दिख रहा है ना, नीला बोर्ड लगा हुआ है, विजन ऑफ द इंस्टीट्यूट, विजन ऑफ द इंस्टीट्यूट। So what is the purpose? The statement help defining the aspirations and remain focused. हमें मालूम है कि क्या करना है, हमारे इंस्टीट्यूट का विजन हमने डिसाइड कर लिया, तो हमें पहले से ही मालूम है कि हमें करना क्या है। या आपको एक सक्सेसफुल मैकेनिकल इंजीनियर बनना है, तो क्या आपने डिसाइड किया है विजन, तभी ऐसा उस डायरेक्शन में चल पा रहे हैं। So the same case, institute also decide a vision. What is the expectation from the graduates or what is the expectations of the our output? जो हमारा जो स्टूडेंट बाहर निकल रहा है उसके साथ क्या सोचा है फ्यूचर में, नियर फ्यूचर में वो क्या बनना चाहता है। So on the basis of different stakeholders means student is the one of the stakeholder of the institute, faculty is the another stakeholder, alumni who is the passed out from the institute, that is also stakeholder, your parents, the student parents, and our industries or employers जहाँ पे job लग रही है। So these are the stakeholders, and sometimes we are using the services of the other academicians, other the experts. So these are the some stakeholders. On the basis of stakeholder, we decide what is the vision of the our institute. So it should be written simple language, easy communicate, and should define the objectives which present the near future of the institute. And vision of the vision statement is the dream of where one want to institute to be and inspire all the stakeholders. हम क्या बनना चाह रहे हैं और हमारे स्टेक होल्डर्स क्या चाह रहे हैं, इस तरह का हम विजन डिसाइड कर रहे हैं। To achieve this vision, we have to follow some steps. To achieve this vision, we have to follow some steps. These steps known as the mission. Mission statements are the actionable statements that guide us, the stakeholders to act. यदि हमें विजन हमने कोई डिसाइड कर लिया, यू वांट टू बी अ सक्सेसफुल engineer. So what is the first action? You have to complete your 10th level first division, then 12 also in first division, then engineering. यदि सॉफ्टवेयर इंजीनियरिंग के बारे में सोचा तो कंप्यूटर इंजीनियरिंग करेंगे, मैकेनिकल इंजीनियरिंग के बारे में आपने डिसाइड कर रखा है, तो दी जाता क्या है, छोटे छोटे स्टेप्स हैं, ये क्या है, मिशन हो गया आपके लाइफ के। या आप वाइस चांसलर बनना चाहते हैं तो क्या करना पड़ेगा, पहले आपको मैकेनिकल इंजीनियरिंग या किसी इंजीनियरिंग में ग्रेजुएशन लेना पड़ेगा, देन पोस्ट ग्रेजुएशन एमटेक, पीएचडी के बाद एक सक्सेसफुल टीचर, उसके बाद एक सक्सेसफुल एचओडी, उसके बाद डायरेक्टर, उसके बाद लेक्चरर। तो ये क्या होगा, स्टेप्स हो गए बीच के। तो स्टेप्स क्या है, मिशन। बीच में उन जो आपका विजन था, उस विजन को आपने बाइफरकेट कर दिया। तो आप अब जब बाहर निकलेंगे इस क्लासरूम के बाद, तो जो मिशन और विजन स्टेटमेंट है वो देखना है। हालांकि मैं यहाँ पे भी एक सिंगल क्लास में दिखाऊंगा, बट आपको ध्यान से ऐसे नहीं चिपकाया गया है सब जगह, वो सब आपसे रिलेटेड, ठीक है। फॉर्मुलेशन में ये कुछ पर्टिकुलर अप्रोचेस फॉलो करते हैं, बॉटम अप अप्रोच। इसका मतलब क्या है, बहुत हमें हाई फाई नहीं सोचना है। ऐसा नहीं है कि हमारी जो कॉम्पिटेंसी नहीं है या हमारे पास रिसोर्सेज नहीं है, उस तरह का हम विजन बना सकते हैं। एनआईटी श्रीनगर को सोचना है तो एनआईटी श्रीनगर के पास व्हाट इज द रिसोर्सेज, what is the possibility, what are the aspirations of the NIT Srinagar या our stakeholders, उसके बेसिस पे हमें अपना विजन डिसाइड करना है जो अचीव हो सके, अचीवेबल हो। Another thing is the brainstorming, discussion, group gap analysis, or you can do SWOT analysis. You heard about the SWOT analysis? It is very important for any organization. What are our strengths, weaknesses, and what is the opportunities, and what are the challenges or threats? So this analysis is required to deciding before deciding the mission and vision of the institute or department. So on the basis of deliberations or the meetings after the brainstorming and as per our strategy plan, what are the strategies, we will decide the vision and mission. So it is clear what is the mission and vision of the institute. Or similarly, there are some guidelines from the NP document. We have to devise what is the vision of the department or institute, what is the vision of the institute. On the basis of this, NIT Srinagar vision, you can everywhere you can find this thing. What is the vision? Our vision to establish a unique identity of the pioneer technical institution for NIT Srinagar. हमारा जो इंस्टीट्यूट है उसकी पहचान हो, इस तरह से हमने सोच रखा है, ठीक है। Developing the high quality technical manpower and technological resources that aid economic and social development of the nation as whole and the region in particular, keeping the view of global challenges. So this is our vision. To achieve this vision, we have to devise few missions. These are the some steps. Okay. After that, how can accomplish these mission and vision of the institute? Because the institute is nothing but it is the combination of all departments or all stakeholders. So bottom up approach. First we have start the department. So same thing. If we discuss about the accreditation, accreditation is not for the institute. Accreditation for the department or particular student. Exactly what is the bottom approach? We want to accredit our student who qualify the outcome-based education standards. So finally, we go for these are the flow chart. These are I have already discussed these are the stakeholders: faculty, industry, parents, alumni. On the basis of their suggestions, we have decided the institute vision. Student is missing here. Why? क्योंकि अभी आप पढ़ रहे हैं, आपको नहीं मालूम कि इंस्टीट्यूट का विजन कौन डिसाइड कर सकता है, एलुमनाई डिसाइड कर सकता है। एंड These are the some stakeholders to decide the vision, and after that, same thing apply for the department also. It is mechanical engineering department vision, and this is the mission. देखा बड़ा ध्यान से पहले कभी तो आप आपको ध्यान रखना है व्हाट इज द रिस्पांस किसकी रिस्पांसिबिलिटी है फैकल्टी की नहीं है पहला स्टेटमेंट क्या था द एजुकेशन इज द स्टूडेंट सेंट्रिक एजुकेशन इज द स्टूडेंट सेंट्रिक सो इट इज आवर रिस्पांसिबिलिटी फैकल्टी को मालूम है विजन डिपार्टमेंट का तो कुछ बदलने वाला नहीं है बदलना किससे है स्टूडेंट्स so we have to understand what are the vision to nurture the mechanical engineers with the passion for the professional excellence who are ready to take the global challenges and serve the society with human values. So बाहर जाके जब प्लेसमेंट हो जाए उसके बाद हमारी ये जिम्मेदारी बनती है कि हमने जो विजन है उसे फुलफिल करना है वहां जाके कुछ अनएथिकल कर दिया किसी से लड़ गए तो हमारा विजन ही फेल हो गया डिपार्टमेंट का ठीक है so another important thing vision के बाद it is the program educational objectives. Program educational objectives is the education objective of engineering degree program of the program. What we want to first few years after the graduation. If we produce the graduates from the department, and what is the our outcome? Outcome is the pass out student, and these pass out student in first few years after graduation. What is the objective? That is known as the program educational objectives. So we have discussed the vision of the department, then program educational objectives. So at the time of accreditation or the visit of the OB related body, they will ask these questions from the student. और हम में से आधे लोगों को क्या मतलब 99% लोगों को मालूम नहीं होता है व्हाट इज द प्रोग्राम एजुकेशनल ऑब्जेक्टिव्स प्रोग्राम एजुकेशनल ऑब्जेक्टिव्स two terms we are using here one is the outcome another is objective what is the difference outcome and objective yes please आप बताओ yes we have discussed the outcome na outcome and objectives what is the difference between the outcome and objective सिंपल मीनिंग से भी बता सकते हैं जरूरी थोड़ी डेफिनेशन ढूंढनी है इसकी ऑब्जेक्टिव yes we are expecting aspirations or desires that is the objectives but exactly kya seek paye that is the outcome so we are not discussing about the objectives only one thing we have mentioned one place of program educational objective but it can be accomplished by the or it will be fulfilled by the program outcomes so next important thing is the after the POs is also framed with the help of the program outcomes and the faculty, student, parents on the basis of all stakeholders, these deliberations or feedback, we can decide the some statement and finally it will approved by the faculty board meeting or the competent authority. Then we will develop the program educational objectives. Okay. So after that, another important thing is the program outcomes. Program objectives is the aspirations, but it is not measurable. Objectives is not measurable. That is the our desires. But outcome is the measurable. With the help of the action verb, we can measure what level of skill, competence, or knowledge. So program outcome statement about the knowledge, skill and attitudes. So whole purpose of this outcome based education is the three main components. First is the knowledge, second is the skill, third one is the attitude or behavior or lifelong learning. So the governing bodies like the NBA, इंडिया के लिए क्या है NBA, हर एक कंट्री के लिए डिफरेंट डिफरेंट था. हमारे यहाँ जो we are using as per the Indian standard So Indian standard, National Board of Accreditation. So National Board of Accreditation decided 12 attributes, 12 parameters that is desired by each and every engineer who is graduating from any part of the India. If they fulfill this minimum standard, the accreditation is provided that institute, otherwise it is failed to achieve the accreditation. So what are the main 12 attributes? These 12 attributes is finally initially decided by the Washington Accord, जिसके हम सिग्नेटरी हैं सारे कंट्रीज. उन्होंने कुछ कॉम्पिटेंसी, कुछ स्किल्स या कुछ नॉलेज related parameters decide किए. So very first four parameter is related to the knowledge and skill. First one is the engineering knowledge. और एग्जैक्टली जो जितना भी हम अभी तक आउटकम बेस्ड एजुकेशन जाने से पहले की बात करते थे या टीचर सेंट्रिक जो एजुकेशन था उसमें इंजीनियरिंग नॉलेज उसमें भी गेन कर रहे थे. तो फर्स्ट टू पैरामीटर्स इंजीनियरिंग नॉलेज एंड प्रॉब्लम एनालिसिस इज रिलेटेड टू द आवर सिलेबस. इट इज रिलेटेड टू आवर जो हमें कंटेंट दिया गया होता है सिलेबस में, सिलेबस है हमारा, उसके बेसिस पे वी लर्न द इंजीनियरिंग नॉलेज, basic laws of engineering, basic laws of sciences, and on the basis of these laws we apply these laws in the numerical problems, and that is the problem analysis. Some simple problems or some designing, modeling, and testing, that is the complex. Another parameter is the design development of solution. Design development of the solution, it is not possible due to the only engineering knowledge. It will be accomplished by the competence or skill. So other parameter, other PU is related to the our skill. And then fourth one is the similar, conduct the investigation and complex problem. Investigation is also possible when you know the fundamentals. You can apply that fundamental in practical manner and you found the conduct the investigation. Next one is the modern tool uses. It is also related to the skill. Different softwares are used कर ही रहे. So it is the software provides the skill set or it is related to the our competence. So first two related to the cognitive knowledge, remaining 3, 4, 5 is related to the our competence. And after that, engineer, society, environmental and sustainability, ethics, these are the related to our behavior. What is the behavior regarding the our engineering, and it is related to the after the being an engineer, what is the need about the environment, what is the need about the society. So we have to inculcate these behavioral concepts. आपका भी वैलिडिटी करेंगे है. जो लेट आए हैं उनके लिए थोड़ा सा फिर से बता दूं, कुछ चीजें हमने कंप्लीट कर ली, बट प्रोग्राम एजुकेशनल ऑब्जेक्टिव्स और प्रोग्राम आउटकम्स ये जिस क्लासरूम में बैठते हैं उसमें भी डिसेमिनेट किए गए और जगह जगह पेश किया गया है. So what is the meaning of the POs, program outcomes, we are discussing. In the first program outcome is the engineering knowledge. Second one is the problem analysis. So these are related to the our engineering knowledge. Means we learn the laws of thermodynamics, laws of mechanics, and some engineering other fundamental laws, and this is the engineering knowledge. And we apply this engineering knowledge in the problem analysis. So these two things we are classroom teaching. Under classroom teaching we are utilizing first two program outcomes. Remaining 3 and 4 it is related to the our competence, skill set. We performing these things in the lab, in the projects, or sometimes some minor project, major project, or seminars. So industrial training. During these we are cover remaining 3, 4 and 5. Fifth is the modern tool use. After that, the engineer and society, environmental and sustainability, ethics. These are the program outcomes. और जो आप प्रोग्राम आउटकम्स की बात कर रहे हैं, ये ऐसा नहीं है कि आईआईटी श्रीनगर के लिए बात हो रही है या एनआईटीज के लिए बात हो रही है. इट इज किसके लिए बात की है? एवरी इंस्टीट्यूट विच प्रोवाइडिंग द ग्रेजुएशन, नॉट इंजीनियरिंग, ग्रेजुएशन, चाहे वो बीएससी का रिलेटेड हो, एमएससी से रिलेटेड हो, इंजीनियरिंग से रिलेटेड, किसी भी ब्रांच से रिलेटेड हो, सभी इंजीनियर्स के लिए, सभी ग्रेजुएट्स के लिए ये इंप्लीमेंट होता है. यदि वो फुलफिल कर रहे हैं these स्टैंडर्ड्स को, देन they get the accreditation. Otherwise it will not qualify. The accreditation will not received by the institute or not institute, particular department. So after that, these are the few other program outcomes. It is also behavior based skill. शुरू में अभी 3 डिस्कस किए थे ना हमने. एक डिस्कस किया था इंजीनियर सोसाइटी, एनवायरनमेंट एंड सस्टेनेबिलिटी, एथिक्स. अदर आर द टीम वर्क एंड इंडिविजुअल. इफ एनी टास्क इज असाइन, तो कुछ लोग ऐसा है कि इंडिविजुअली बहुत अच्छा काम कर सकते हैं और कुछ एज ए टीम काम कर सकते हैं. इंडिविजुअली हाथ पांव खुल जाते हैं. सो इंडिविजुअल का मतलब एज ए वी हैव टू डेवलप द स्किल. इफ द सिचुएशन, कभी कभी सिचुएशन ऐसा नहीं है कि आपको हर बार टीम होगा ही. आपका कोई प्रॉब्लम, इंडस्ट्री में वर्क कर रहे हैं, कभी भी एक्सीडेंट की कंडीशन आ सकती है, कुछ सिचुएशन क्रिएट हो सकती है. सो दैट इज द रिक्वायरमेंट ऑफ द एनी इंजीनियर हु कैन फेस द इंडिविजुअल एज वेल एज द टीम वर्क. एंड टीम वर्क के साथ में जरूरी क्या है? एज ए टीम मेंबर और एज ए टीम लीडर. ओके. आफ्टर दैट अनदर इंपॉर्टेंट थिंग, ये तो सभी लोग समझ ही रहे हैं, इसका तो बहुत रोल है. आपको बहुत कुछ मालूम है, कम्युनिकेट ही नहीं कर पा रहे हैं, देन देयर इज नो मीनिंग ऑफ दैट knowledge. That is not outcome based education. Outcome based education, if you know something, then you can communicate this knowledge to others. And project and finance, finally सारा कुछ इसी के लिए होता है. So we have to know how can minimize the waste, how can minimize our losses, can improve the efficiency. And another thing is the finance or money related, where how can save the money. So these are the set of the skills or set of the attributes is desired in every engineer. And last one is the lifelong learning. ये हमने शुरू में बात की थी. यदि कोई चीज आपने पूरी तरह से कॉम्पिटेंस को बार-बार प्रैक्टिस कर रहे हैं, बार-बार प्रैक्टिस कर रहे हैं, तो क्या हो जाएगा? वो स्किल आपकी लाइफ लॉन्ग लर्निंग हो जाएगी. जैसे कार का एग्जांपल बताया था. ठीक है. अब बात ये होती है कि हम तो मैकेनिकल इंजीनियर हैं, कुछ लोग सिविल है, कुछ इलेक्ट्रिकल है, कुछ हो सकता है कंप्यूटर साइंस इंजीनियर, और सभी पे ये कैसे इंप्लीमेंट हो जाएगा, या सभी के लिए एक सारी चीजें कॉमन कैसे हो सकती हैं? सो दीज आर द कॉमन, एक्सेप्ट दिस सम आउटकम्स आर द स्पेसिफिक पर्टिकुलर प्रोग्राम. प्रोग्राम का मतलब डिपार्टमेंट से है. Three the words are utilizing here. One is the institute, you everyone know. Another is the program. Program is the department. We are not using the word department. Department के जगह क्या use कर रहे हैं? Program. And another word is the course. Course क्या है? Course is the subject. After that, bottom to up approach है. So initially start कहाँ से होगा? जो आपको subject पढ़ाया जा रहा है. So course is the subject. So in the PSO, program specific outcomes. If we are studying in the mechanical engineer, so we can decide some outcomes related to mechanical engineering. Our department PSOs are there. It is also disseminated everywhere. In department you can see mechanical engineering department में जब इधर-उधर आप मूव करेंगे तो दिखाई दे जाएगा. पहला PSO क्या है? पहला program specific outcome. Apply the knowledge of the basic sciences, मैथमेटिक्स एंड मैकेनिकल इंजीनियरिंग टू रियल लाइफ प्रॉब्लम्स. यदि कोई चीज सीखी है तो हमारा आउटकम क्या है कि हम उन्हें रियल लाइफ जो कंडीशंस है उन्हें अप्लाई कर सकें. Another thing, inculcate the advanced level of skill in academics and research pursuit relevant to the mechanical engineer and other interdisciplinary streams. अभी आप देख ही रहे हैं क्योंकि ऐसा नहीं है मैकेनिकल इंजीनियर मैकेनिकल रिलेटेड इंडस्ट्री में जाएगा. That is the interdisciplinary. So if the interdisciplinary, then we have to develop our graduates in such a way that they can have such competence, they can accommodate in the other industry also, other discipline also. And last one is the ability to integrate the major mechanical engineering streams with the innovative and entrepreneurship activities, ensuring the high standard of professional ethics. So overall, develop a graduates, but with high level of professional ethics. The professional ethics is required. कोई भी चीज हम डिजाइन कर रहे हैं तो केवल इसलिए नहीं डिजाइन करते हैं जिससे कि हमारी जो रिक्वायरमेंट है वो फुलफिल हो जाए. Our main focus is the safety of human being. जिसके लिए डिजाइन हो रहा है सबसे मेन प्राइम कंसर्न क्या है? कॉस्ट नहीं है प्राइम कंसर्न, हमारी एफिशिएंसी नहीं है. सबसे ज्यादा प्राइम कंसर्न क्या है? प्रोफेशनल एथिक्स मींस उसकी वजह से किसी को हैजार्ड नहीं होना चाहिए आइदर एनवायरनमेंट और ह्यूमन में.
I'm getting bored. Director can just
Okay, no issue. My lecture is too long, so there is as per the program coordinator or the I will stop here. But meanwhile, you can ask us some questions. That is the better because it is a very long topic.
Any questions from the audience? Sir, thank you.
Yes, 1 second. एक चीज मैं और दिखाना चाह रहा हूँ, पहले वो देख लीजिए उसके बाद थोड़ा सा क्योंकि हमारा ऑब्जेक्टिव था क्या आउटकम बेस्ड एजुकेशन का, वो देख लेते हैं. This is the framework. Means what is the outcome based education? On the basis of outcome based education, we design the curriculum. Curriculum means overall, not on this level. Curriculum, then outcome based teaching learning process, and finally our assessment process is also related to the outcome based. If we perform something and how can measure the activities of the student, so final is the outcome based assessment. So this is the framework of the outcome based education. हमें अपने सिलेबस को कैरिकुलम को इस तरह से डिजाइन करना है कि वो आउटकम बेस्ड हो. फर्स्ट लॉ ऑफ थर्मोडायनामिक्स पढ़ाने से काम नहीं चलने वाला. फर्स्ट लॉ ऑफ थर्मोडायनामिक्स का इंप्लीमेंटेशन एप्लीकेशन पार्ट और वो विजुलाइज कर सके स्टूडेंट. साथ के साथ यदि वो विजुअल उसको परफॉर्म करना है तो उसका असेसमेंट कैसे होगा. फॉर एग्जांपल किसी ने कोई एक्सपेरिमेंट कर दिया पर उसको हमने, क्योंकि हम असेसमेंट किसके बेसिस पर करते हैं हमेशा, मिड टर्म एंड टर्म की बेसिस पर, तो दैट इज नॉट फीजिबल. यदि आउटकम बेस्ड एजुकेशन की बात कर रहे हैं तो आउटकम बेस्ड जो परफॉर्मेंस है उसको भी असेसमेंट करना है. तो फाइनली 4 स्टेप्स आर देयर. आउटकम बेस्ड एजुकेशन, देन करिकुलम, देन outcome based teaching learning process, finally outcome based assessment process. Yes, please ask the question.
So generally we have program outcomes and program specific outcomes.
Yeah.
Sometimes it becomes very difficult to differentiate how they different from each other.
Okay. The program specific outcome is the subset of the program outcomes. Program outcomes का सबसेट ही है जो स्पेसिफिक आउटकम कुछ अलग से नहीं है. या फिर विजन और ये सारी चीजें जो भी डिजाइन कर रहे हैं वो ओवरऑल जो हमारा अकॉर्ड बना हुआ है जिसे हम बोल रहे हैं, जिसके रिस्पेक्ट में एनबीए वर्क कर रहा है, वो उसका सबसेट है टोटल. यस हाँ, यस एग्जैक्टली, वेरी गुड क्वेश्चन. अभी हम क्या कर रहे हैं, जैसे पिछली बार फर्स्ट किया था डेटा या हमने मैनिपुलेट करके बनाया था, वैसा कुछ नहीं कर रहे हैं. वो मैनिपुलेशन की वजह से ही किसी भी डिपार्टमेंट को एनबीए नहीं मिला, क्योंकि वो लोग जो आते हैं ऑब्जर्व करने उन्हें उसी फॉर्म में ही देखना है. सो अभी हमने इस समय जो लोग मैकेनिकल के स्टूडेंट है उन्हें पता लग गया होगा, सारा प्रोसेस ही चेंज कर दिया है. कंटिन्यूअस असेसमेंट हो गया है, मिड टर्म घट गया है, मैं इंटर्न का वेटेज भी घटा दिया है, कंटिन्यूअस असेसमेंट का वेटेज बढ़ा दिया है। ठीक है, आउटकम बेस्ड एजुकेशन के हिसाब से ही हम चीजें डिवाइस कर रहे हैं, और साथ के साथ एक सॉफ्टवेयर भी लाए हैं, उस सॉफ्टवेयर में डेली बेसिस पे वो चीजें फीड भी कर रहे हैं। तो अभी वैसा नहीं करेंगे प्रीवियस ईयर। और कोई क्वेश्चन? कैरिकुलम में काफी कुछ चेंजेस किए हैं। कैरिकुलम में देखिए सबसे बड़ा एक चेंज है, हमारे पास पहले हमारा 8 सेमेस्टर तक का कैरिकुलम होता था, उसमें सारे सब्जेक्ट 8 सेमेस्टर में काफी लोगों ने आईसी इंजन और पावर प्लांट जैसे कोर सब्जेक्ट भी पढ़े होंगे। अब वो सारे सब्जेक्ट 6 सेमेस्टर तक ही कवर हो जाते हैं। एक तो ये, दूसरा हमने ओपन इलेक्टिव स्टार्ट कर दिए। ओपन इलेक्टिव स्टार्ट मींस आप पाइथन पढ़ सकते हैं, आप डेटा स्ट्रक्चर पढ़ सकते हैं, मतलब दूसरे डिपार्टमेंट के सब्जेक्ट पढ़ सकते हैं। हमने स्वयं से रिलेटेड 10 क्रेडिट का कोर्स, 10 क्रेडिट मतलब 4 कोर्सेज तक के लिए फैसिलिटी दे दी, और साथ के साथ 6 महीने का इंटर्नशिप दे दिया। I request now Professor Wani to illustrate. Thank you, sir. Actually, all registered participants have filled this feedback. ये आज का लेक्चर का आउटकम भी है, जितना हम आउटकम बेस्ड एजुकेशन की बात कर रहे हैं ना, तो आउटकम बेस्ड एजुकेशन वाला ओनली रेजिस्टर्ड पार्टिसिपेंट्स। एलईडी के बाद में लिखिए जो पहले आउटसाइड से वो लिखिए। हां ये तो स्टार्ट करते हैं सर।
Okay, we have just circulated online Google Forms to you also. Please fill those online. It is having MCQs, huh? No. That tells them. Itu Pak Aku sorry sih. Aspal. Ah. Because we are thinking now. Oh, we check. Because I think क्या feedback क्या बोलते हैं? Feedback तो दिया था। So I invite the participants. They have to say something about the workshop FDP. So they can come to the stage and
आपने इसको 5 दिन में बहुत कुछ सीखा है, तो उसका एक्सपीरियंस है।
आप लोग भी बोलेंगे अच्छा हाँ सभी बोलेंगे स्टेज में हिंदी में बोलना दोनों लैंग्वेज में बोलना चलो अब जैसे आप कश्मीरी में बोल इंट्रोडक्शन अपना हेलो ये नहीं चलता ये चलता है हाथ में देखिए ये क्यों नहीं चलता भाई आता शो तो मैंने क्या बना सेंसर ही नहीं मिले आप फोटो कीजिए सेंसर है ना ये वो है ही नहीं आरएफआईडी है ही नहीं
हेलो 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 hello my name is Alok Ranjan Yadav. I have come from Lucknow, Uttar Pradesh, and I have completed my MTech in mechanical engineering. I was in search of PhD, and since useful for that because it has given me an insight into the mechanical engineering aspects of the working of all the things that I've seen in my courses that were mostly theoretical. And on the behalf of my great experience, I first of all like to thank AICT, NIT Srinagar, and especially Professor Adnan Kayyum sir, who has conducted and organized such a wonderful FDP, which was really useful. And the learnings that I take from here are just not related only to the subject part, but also to the new geopolitical aspect of the things that I've learned here. Will be useful for things that whenever I go and back to my place and speak about it, it will give and try to clear up a lot of some predispositions and prejudices of the people around where I live. Thank you a lot, NIT Srinagar Mechanical Engineering Department, and every last of the participants and the fellow participants and the students who were part of this activity along with me, who enriched my knowledge and learning with this thing. Thank you. Thanks a lot.
Anyone else? आप आपका सीनियर आप बोलेंगे कुछ? ये भी बोलेंगे, ये भी बोलेंगे। फीडबैक लेना, फीडबैक
कुछ भी
Assalamualaikum and good afternoon everyone. ये FDP था तो फैकल्टी डेवलपमेंट प्रोग्राम, बट मैं कश्मीर यूनिवर्सिटी से हूँ, बीटेक कर रही हूँ, 7th सेमेस्टर IOT, एंड था तो ये फैकल्टी के लिए, बट इट वाज वेरी इंफॉर्मेटिव एंड बहुत कुछ सीखा, बहुत कुछ देखा, बस।
Balsa Abbas. चलो उठो। माविश बोलो इसके बाद आप, हाँ ठीक है ना फीडबैक। बिजनेस का बोलना, बिजनेस डिस्कस करना। एमटेक सर को, कौन से एमटेक सर को एक हाँ हाँ ये वो राइट बात है।
यही तो रियली आउटकम है। आज का लेक्चर लास्ट किसी को कराया गया था।
वो बॉडी का विजन बोलो ना कैसा था।
आप कुछ थोड़ा बोलेंगे तभी तो।
आप कौन सा विजन?
Myself Farha Yusuf, I am pursuing FTech Information Engineering from NIT.
ये तो आपके लिए
कौन सा सेशन अच्छा लगा, क्या क्या अच्छा लगा?
सब कुछ अच्छा था, जितना भी बहुत सारा जो भी इंफॉर्मेशन भी हमारे प्रोग्राम किया गया था, इसमें सारे सेशंस थे वो बहुत अच्छे थे। हमें बहुत इंफॉर्मेशन नॉलेज फ्यूचर एप्लीकेशन करेगा, बाकी आगे क्या कुछ करेंगे उसके लिए।
अच्छा, एक बोटलिंग प्लांट देखने गए थे। क्वेश्चन सभी के लिए है, पहले ये बताएंगे उसके बाद और बताएंगे। बोटलिंग प्लांट में दो तरह का एलपीजी को मूवमेंट दे रहे थे, एक था लिक्विड एलपीजी, दूसरा था वेपर एलपीजी। क्या कलर कोड क्या था, लिक्विड का और वेपर का? अरे सर ये आउटकम है सर, मतलब सीखने गए, देखने क्या देखा, क्या क्या थे कलर कोड? ऑरेंज किसके लिए था, रेड किसके लिए था? देखा था ना सर ने? हमारे बॉयज जो है इतने ज्यादा आते हैं सब खराब है दुलावर
मैडम आप बोलिए। आप बोलो आज कौन जम्मू वुमेन्स कॉलेज जम्मू गवर्नमेंट वुमेन्स कॉलेज केमिस्ट्री डिपार्टमेंट
A very good afternoon to all. This is Dr. Gurpreet Kaur. I am assistant professor in chemistry, Government College for Women Parade. It was a wonderful experience to attend this program. I have already attended many programs sponsored by Kashmir University, but got this opportunity for the first time to visit NIT after it had been REC at one point of time. I joined here as a civil engineer in 2002. Uh, got, yes, 2002, it was REC at that time.
okay
I qualified like a CT, joined here as a civil engineer, but I was the only girl in my class out of the 60
then
students.
you left
Then I left it after 2 months. And after that, I got this opportunity to visit here as an IT. And it was wonderful and I missed it. I wished I could have not left it. लेकिन अब मुझे लग रहा है कि अच्छा होता अगर शायद मैंने की होती इंजीनियरिंग but it's good to interact with the young students and I must appreciate the hospitality of Adnan sir. He is the most ever cool HOD I have ever seen in my life. Otherwise, HODs that too from engineering background, they appear to be quite dreadful. But during online session, I enjoyed his online talk,
assalamu alaikum
and he's the ever cool person I have known. Thank you very much, and I thank you.
thank you anyone else
Thank you, Dr. Pali sir, for such an informative lecture. Now I request Professor Adnan Tayoum to give a brief report of the faculty development program.
Respected Professor M. Afwani Saab, Professor S.K. Bukhari, Registrar NIT, Dr. Shahid Salim, Dr. Mohsin, Dr. Parvi, colleagues, participants, and dear students. Assalamu alaikum and good afternoon. I, on behalf of Mechanical Engineering Department and the organizing committee, welcome you to the valedictory function of the FDP on thermal characterization and advanced measurement techniques. We have just completed a 2 week hybrid blended program having both online sessions and offline sessions. Online sessions of FDP were successfully completed from March 13 to March 18, and offline sessions at NIT Signal started on March 20 and have now been completed today. So lectures were delivered in the online session from IIT by experts from IITs, NITs, and for the offline session we had experts from our NIT, Kashmir University, IUST, IIT Roorkee, and today we had a speaker from industry also. They also delivered talks. So the offline sessions of this FDP again were exhaustive and comprehensive, just similar to what we had in the online session. So actually, this FDP, I just tell, I had this FDP just for MTech Tamil students because we started that course last year. Actually, all the topics which I have chosen in this, they were meant for those MTech Tamil people. I hope they have just gained good insight of what they have to study in thermal engineering at PG level. Okay, so our thermal students were exposed to advanced fields like experimental and computational fluid mechanics, renewable energy, energy management, some latest techniques, optical measurement techniques like LCD, infrared thermography. Today they had a feel of how they can just use laser diagnostic tools for experimental fluid mechanics. And in addition to these things, we had 3, 4 lectures which were just focused on national education policy, developing good skills for teaching and education. In this FDP, we started with an industrial visit to HPCL bottling plant. And in fact, that visit to bottling plant laid a very strong foundation in terms of state-of-art techniques involved in measurement, automation, in real-world situations. So this was followed in subsequent days by several lab visits. One such lab was in advanced manufacturing section, so where the students were exposed to how they can design and manufacture state-of-art complex models, accessories for their research and subsequently measurements. So day before yesterday, our participants had a very detailed visit to Central Research Facility, uh, and they had a very exciting hands-on training session on various equipments. The session was conducted by Dr. Nadeem under the supervision of Professor M. Fani. So all these sessions were highly interactive, and I'm hopeful that each participant was satisfied by the reply of the experts. So all these sessions were streamed live on our Institute YouTube channel and are now available for offline viewing. I hope that during the online, offline lab visits, industrial visits, the participants have become familiar with the latest measurement and measurement tools which is the need of our. In the end, I am confident that some sort of networking has been established between the participants and the resource person, and maybe it may lead to collaborative work and will benefit all of us. Finally, I hope that the participants had a nice and wonderful time here at NIT Srinagar. May God bless us. Allah Hafiz. Thank you.
Thank you, Adnan sir, for giving us a brief report of the event. Now I request Professor M. Wali to be here and address the audience.
Thank you very much. God bless you. Good afternoon to everybody. It is a great pleasure that our department has successfully conducted this FDP under ATAL program of AICTE. And pleased to have here my HOD, Professor Adnan, Dr. Sheikh Said Salim, Professor Fani Saab, Dr. Mosi, and other colleagues, and Registrar Saab, Professor Bukhari. While when I was approaching this hall, I was limping on the staircase. So I went back to 1984 when I was 20, 79. I used to jump over 3 stairs at a time. Now, you know, there is one stair, it's very difficult. So things move on very fast and still, as if I was a student here yesterday. But I will tell you one thing that you must identify your goals right from the beginning. What do you want to do in life? You want to go to the teaching, then plan accordingly. You want to go to industry. We did not have these things at that time. To be frank, in fact, we were thinking after BTech we have to go to the jail and in the hostel we had a rule that after 9 p.m. nobody should put on the light because there should be no reading in the hostel. So we were a group of students who never wanted to study because we had become JE, but now things are competitive. We have to face competition, but this time is much better than that. I will tell you. If you put me as a student here, I will be in 4 years in NASA. I will tell you. Even at this age, I'm telling you, because such are the capabilities, not in me, but the teachers and facilities which are available. You must take full advantage of the facilities, because nowadays the technology, the innovation, the ideas have reached to such a level you cannot imagine. I feel at this time that I should have been a student because I would learn more from my teachers what is latest. And this thing is available with you. Now I cannot go to any class of FEM or any class of additive manufacturing and then think of microstructures and materials. We are still striving to reach the highest level of journal publications in the department, in the mechanical engineering department. Though we have facilities because maybe we will achieve that. So this FDP, while we have seen various things in the department, uh, you are lucky to have such facilities in the department. I have seen once only UTM test in civil engineering when we were BTech students. And we were taken once and we were shown at a distance that this is the UTM test and this is the flexible failure. We had never seen machines in the NIT system. This lab was first made, I think, in the 90s, material testing. But we had good teachers. I must admit that their theoretical knowledge was very sound and students were serious. Whatever they were studying with seriousness. And I know the department is progressing by leaps and bounds. We have, we are lucky to we have accreditation of our department, and it is up for new faculty now to see that they carry forward. They have a challenge. They must not think it's the easy thing now. If they want to stand somewhere in the country, people have to work hard. I must tell you that people have to see that they are present in the department day and night. Then you can struggle with the other departments of the country in the mechanical engineering department. And if we don't have that uh, zeal and just a working environment or that potential in ourselves, we must not strive that we are not among the leading institutes, among the leading departments in the country. We must bring name to the NIT. People must know the mechanical engineering department. Then they can get good jobs anywhere in the world. So if our faculty who is now new, they are very young and they have potential, they have come through competition now to all India level, and I must say that they have the potential, but they have to only accept. Same is the case with the students. FDPs teach you that where we stand and what are our capabilities in the department, whether it is theoretical knowledge, whether it is experimental use of equipment or developing materials. But I'm telling you, our students don't utilize the facility, they don't get the patents. Otherwise, our department can get at least 100 patents in a year if the students and teachers work properly in the proper direction. Because the facilities which we have to do small things to file a patent, nothing much. But it must be innovative. Things are moving very fast, and some faculty members here file 12 patents in a year. Why not a department which has 105 students cannot file patents? We have money, everything is there. Satsang is doing work in this direction. But I hope this FDP might have taught you very good things. And there were teachers from outside. Though I did not have time to talk about something new. In the case of innovation, system design, now I'm an old man because sometimes old men talk too much and they talk also irrelevant. And people say that these are now old people, they have nothing to do. They will spoil their time. So I think that we are here, and I must tell you, we are here for students. I become very happy when student comes to me that I want to do this thing here. एंड दो चीज़ें मैंने एनआईटी में बहुत चीज़ें देखी है यहाँ एक चीज़ तो मैं एम्प्लॉयज़ के बारे में कहता हूँ हर एक एम्प्लॉय कहता है कि मुझे जाना है सवेरे लेकिन आज तक इस 35 years ऑफ सर्विस में किसी एम्प्लॉय ने नहीं कहा मैं कल भी आऊँगा यहाँ मुझे काम है मतलब दो और स्टूडेंट भी ऐसा नहीं है कोई जो मुझे कहे तो मैं रात भर यहाँ बैठूंगा काम करने के लिए ये चीज़ें बहुत इंपॉर्टेंट है तो अब तो ये चीज़ें हैं आपको करनी है अगर आपको कहीं बाहर जाना है मतलब एडमिशन के लिए किसी अच्छी यूनिवर्सिटी में you have to show matter. We have our students get admission today. Our student got admission somewhere. Must not can disclose it here in a very good university. But we have to also think in that direction. My dear students, you have time, you have potential, you are intelligent. We were not so intelligent at our time. I think because of that, we could not go USA, but at that time or somewhere else, we went to IIT, but we did better there also. But we have got open world at this time. And if you go anywhere in the world, I think you should be accepted with open hands and open arms. I recently evaluated one university from advanced country, PhD, and I thought the work is as good as ours. I must tell you, I was very proud to see that they also don't do such a thing which we could not do in our laboratory. So I must I have confidence in that. So I also feel we have very brilliant students in our mechanical. I always feel the students of mechanical, the faculty of mechanical is very brilliant. Some of our faculty members you don't know their potential. But I told in the beginning also, they have very good potential. And if you know how to get best, that's up to you. So with these words, I must congratulate the HOD, the director, Mr. Sahab, and other faculty members who are doing work at this time out of and these extracurricular activities, FDPs. My message to all students and faculty is that they must see that our department is best, not in the NIT only, but in whole India. Thank you.
Thank you, sir, for such encouraging words. Now I request Professor S.K. Bukhari, Registrar NIT Srinagar, to come to dais and address the audience.
Professor Vani, in charge director NIT Srinagar, Professor Arna, Dr. Shahid, my two friends and coordinators of this workshop, young faculty, participants from different institutions, and my dear students. Very good afternoon to all of you. I'll ask you a question after conclusion of this 15-day, this FDP. Which is the toughest profession? No, it is teaching. It is teaching. Why? Say in this hall there are 60 students and I am teaching, I cannot satisfy all of them. So my teaching may satisfy 10, 20, some percentage, but I cannot satisfy 100%. So you have to be abreast with the latest knowledge and techniques. And in today's era, when there are different search engines, including Google Auntie, you will be teaching something and students will search there and they will object you. So in these circumstances, teaching is very tough, and it is getting tougher day by day. So for that, you need to accelerate. You need to know your research. You need to know the research around the world. This one. Second, as Professor Farooq said, that we found the machines in civil engineering only. Do you know earlier there were only two engineering branches, civil and military engineering. Your mechanical engineering and other engineering branches came out of military engineering. Civil is Uh, we call it as thumb rule engineering. थंब रूल इंजीनियरिंग मीन्स कि आप घर में हैं, आपने सीमेंट लगाना है, लगा यार इतना एक बजरी डालो, एक सैंड डालो, एक वो आधा सीमेंट डालो तो हो गया, मिक्स कर दो तो एक M10 बन गया. We call it as thumb rule. When I joined this institution in 1999, there was a batch. हमने तो उनको नहीं पढ़ाया, student from electrical engineering. After some 10 odd years, we met somewhere in some marriage. He told me, sir, engineering तो civil है. मैंने कहा क्यों तुम electrical engineer? वो अक्सर क्लास में आते थे teacher, they would say that this current is passing the magnetic field. Another teacher came, he told me it is coming through the conductor. ना कंडक्टर में दिखी ना मैग्नेटिक फील्ड दिखा. मैं as assistant engineer, I have been assigned the task of construction of these towers. तो वहाँ पे तो इंजीनियरिंग है यार, इतना सैंड लगेगा ऊपर है सामने है, इतना सीमेंट लगेगा सामने है. So that is why it is thumb rule engineering. And without infrastructure we cannot do anything. Once we construct building, then you can do mechanical engineering. There are different gadgets, equipments, you can place them there. But as Sir said, that at that time civil engineering of REC Srinagar was, I suppose, second the famous department in Asia after this Roorkee, University of Roorkee, which is now IIT. I hope these 15 days have given you some insights and hands-on the lab which has been developed by Professor Vani. And as in my inaugural address also I told that there are such 5 labs only in the country, and we are proud to have one such lab. Obviously, you might have got exposure to different machinery, to different equipments, which will you take forward to your students. With these words, I once again congratulate Professor Adnan, Professor Shahid, and the young faculty of Mechanical Engineering Department who have delivered talks for the speakers who were from IITs or NITs, and you might have taken some lead, some insights which you take forward to your students. Thank you.
Thank you, sir. Now I request Dr. Sheikh Shahid Salim and Professor S.K. Bukhari to come on the stage for felicitation ceremony. The first certificate is for Gautam. The second certificate is for Tawfiq Mushtaq Shah. The third certificate is for Prab Karan, Rajbir Singh. Ayushi Chaudhary. Rinchan Dolma. Habib Jasti. Kushan Kari.
And Sheikatu Sajjad. Thank you so much, sir.
Okay, thank you everybody. We'll just conclude with this session, the session. Thank you all for being here, for the participants. I hope We had a great time in learning, and also to Professor Mifani, Professor Srinagar, Professor Dan Kuyum, Dr. Pali, and Dr. Mohsen, and all the other staff and students who basically organized all of this lectures. It was a painstaking effort. Well done to all. Thank you so much, and see you next time, hopefully next year.
Registered participants will stay here and attend. Okay.